let's start. So, as I told you, LIFE PlasPLUS is focused on the recycling of high-quality secondary plastics and the critical raw material antimony coming from WEEE and ELVs. It's a LIFE project financed by Europe. So first, welcome to Comet Traitements. So normally you should visit us at Aubourg, but I will do this presentation right now. Comet is an industrial company, a family company involved in the recycling of metallic waste mainly. We are mainly active in France and in Belgium, with two major sites in Châtelet and Aubourg. To recycle the residue that I will present after, we have 8 what we call PST plants, post-shredder treatment plant, to treat the light and heavy shredder residue fraction. We are 400 workers roughly, and a strong R&D team of more than 15 people. If we speak about highlight figures, we treat around 1.2 million tons of metallic waste per year, and we achieve a recycling rate of 97.8 recycling rate on the ELV. So it's very strange that we are here talking about plastics, and our core topics is metallic waste, like you can see now. But as you know, the metallic recyclers are also facing with 2 other materials. That means the ELVs and the WEEE. As you can see in this table, if you want to reach the European objective for recycling, if you want to recycle correctly ELV and WEEE, you have to face with the plastic stream, representing around 17% in the ELVs and more than around 20% in the WEEE. So it's key topics to deal with to reach the targets of Europe. So I have to just to present in a short time what we call shredder residues. The ELV cars, when they arrive by Comet, need to be treated at the first step, as we call a depollution center. By Comet is Resicar. At this step, we will make the depollution. We will put away batteries, cars, all the liquids to prepare the vehicle to be recycled. And of course, for the W3E, we have to respect a list of depollution we have to do to be in line with the WEEE regulation. After the depollution, we can start to shred the material. And the first step after air suction is to do a magnetic separation, and we separate the shredded iron. And depending the air suction, we create 2 waste, the light fraction and the heavy fraction. We will discuss today about the plastics that we are finding in the light fraction and in the heavy fraction. Both materials are treated and recycled by Comet Traitements. Just to illustrate, that's the kind of equipment we have on site. For example, here the shredder at Aubourg that you should have seen today is a 7,000 horsepower shredder able to shred 300 cars per hour. All the shredded iron is gone to steel industry by boat mainly. So now, if we spoke about the mass balance of a shredder, you can see that on average, we are recycling between 70 to 80% of ferrous fraction that goes directly to steel industry. And we have to fraction the heavy shredder residues and the shredder residues. Those 2 flows represent around 10 million tons per year, or what we call a renewable ores. That's the ores that we are recycling by Comet. You have to know that until the 90s, mainly it was all mainly landfilled, and now with long work of R&D and new development, we have reached a recovery rate over the 95%. So to reach this high level of recycling rate, we will have to develop several post-threader technology to be able to separate and valorize several kind of materials. The plastics, of course, we will speak this in detail after, but we have also all the non-recyclable organic material like wood, foam, and some other organic material. And for this, we have a project process of catalytic cracking to produce electronic fuels, energy, and char that we will use also in the LIFE PlasPLUS project. I will explain it later. We separate also iron oxide for the cement industry. As you know, for example, in the car, you have a lot of glasses. We recover this glass to produce a technical sand to use it in bituminous concrete, use it in motorway construction. And of course, one of main core business of Comet is metals. Like I explained you, we have a lot of non-ferrous metals, and this is, we produce robotic something to separate high pure fraction of non-ferrous metals. And so with this figure, we reach the recovery rate of 97.8% of recovery rate on ELVs and shredded residues. And here we present the rough figures of the distribution of several materials that we are recycled. Now, what about the plastics in the shredder residues? When we start the R&D on this material, see what we have in the plastic, in those kind of material. We have absolutely everything, every kind of plastics you can imagine in car ELVs, in W3, and also in the scraps iron. And we have plastics and thermoplastics, but we have also thermoset, elastomer, silicones, and wood mixed together. So the idea was to recover first from this big mixture of heterogeneous mix of plastics to produce purified PP, PA, ABS, PS, the four major plastics we have in this stream. Of course, the goal is to close the loop with what we call circular plastics, because we come back in the same application, like I will explain after. And now we, since 2012, we start a line, what we call the plastic PST plant, with a capacity of treatment of 85,000 tons per year of mixed plastic streams. To explain what we are doing, so we receive, the plastic plant receive concentrate of thermoplastics and rubbers, and we do several steps of recovery and purification. We do mainly density separation, and density 1, we recover all the polyolefins, that unfilled polyolefins that we call PP3, Comet Traitements. And the sinking fraction at 1 is separate a new second time at a density of 1.08 to recover what we call the ternary plastic mixture ABS, PS, and FPP. This stream is one target of the LIFE PlasPLUS project, and I will explain you after the challenge of this. And why we cut at 1.08 is because we have to respect the RoHS directive about the brominated flame retardant. At this density, the brominated flame retardant plastics are concentrated in the sinking fraction. This sinking fraction is now called DRENA+, and it has a using as material used in landfilling to collect the lixiviate and the leaching and the biogas in landfilling to manage those liquids and gas in the landfill, because the porosity and the permeability of those materials is the same as natural crushed stones. This DRENA+ is also one of the input material of the LIFE PlasPLUS project. So I go now directly to the core of this presentation, this LIFE PlasPLUS project. So this project location is in Belgium, in Aubourg, because it's there that we put the demonstrator to separate the ternary IBS, PS, filled PP demonstrator for a budget around 3.2 million euros. We start in July 2009 and we will finish this year. We are 5 partners: University of Liège, the Stellantis group with the Center of Research of Fiat, the Belgian company CAMPINE, and the compounder STELLANTIS in Italy. So I will not go shortly in details. Normally we do it, but we are pleased to welcome today Charlotte. So I will not go in details of the plastics matrix because it's the goal of Charlotte. But the key is to see that ELV and the transportation usage for the transport is a lot of tonnage, respecting 19 million tons and 29 tons respectively for those 2 sectors. So it's around 15% of what we are using in cars and electrical appliances. So it's large volume. But I will directly do this slide because you can see exactly what we call a mixture of plastics coming from ELV and WEEE. That's the material that we are recycling every day by Comet. So on the right, on the left, sorry, you have the plastic string coming from WEEE, and on the back, the right side, you have the ELVs and coming from classical shredder residues. So what is specific for the LIFE PlasPLUS is the concept, because we have an holistic approach to close the loop systematically for 2 traditionally isolated materials value chain. It means that we are focusing on plastics, to recycle plastics, but also a mineral fraction that is the antimony. So by high purity recycling, it means that we will focus mainly here in this case on ABS and FILPP, and the antimony because it's also a critical raw material for Europe. So what is important, that the key of the LIFE PlasPLUS project is the partners and the whole material value chain that we want to present. It means that we go directly from the recyclers with waste sorting and valorization that we do by Comet. R&D will be done by University of Liège, and we have CAMPINE for the production of antimony with the trioxide that we will purify by Comet and University of Liège. STELLANTIS is all compounders. They will receive the purified ABS and PS separated by Comet. And Stellantis, the group Stellantis and CRF will use this, will suggest what the data sheet they would like to receive from STELLANTIS to produce automotive parts with the compound produced by this value chain. And also in the valorization, the goal of CAMPINE is to produce a flame retardant master batch with the antimony that we will recover from the project. So I will not detail all the objective that we have listed here, but that's all what we have to do for this project. But the key for us is the substitution, the target on the substitution of virgin plastics. The target is to produce secondary compounds with more than 40% of substitution of virgin plastics. And of course, the key is to demonstrate that those compounds can be reused directly in automotive parts, and so we close the loop. We confirm the circularity of the global value chain. Now, to reach this target, I will explain you the flow sheet and the step of this project. So, on the first step is I will explain you that we have done for the existing infrastructure that we separate the ternary mixture of ABS, PS, and mineral field PP. So the step 1 is to be able to separate those 3 streams, but complicated streams because the state of the art is only to separate binary mixture, maybe IBS and BS and PS mixture, but in our case, as our main target, the main flow is using a lot of FPP, max around 25% of FPP in the ABS-PS mixture. We have to face to a problem that no supplier can give us those kind of technology to separate these three plastics in one step. So we develop this demonstrator unit to demonstrate our process on large quantity of PS, ABS, and FPP. That's the pilot that I would like to show you maybe next for the second dedicated event when you could visit Comet. So I show you here the two qualities of the product that we produce with this demonstrator. That's the FPP for fillet PP. Mineral, so it's filler is mainly mineral, it's the mineral fraction, mineral filler mainly talcum. And on the other hand, you have the ABS PS regrind. Samples are already sent, of course, to Cereplast for this first compounding trial. What is very important for recycling to reach high value compounds is the purity of the material. So our target is to reach and to be above 98% of purity for each fraction. You can see that for the FPP, we are around 99% of purity of fillet PP. And for the IBS, we are on 98. Those quality is validated by Cereplast. What is also important that I told you that we have to take care about ROHS value. Of course, the first thing that we do is to check that we are okay with the limit of brominated flame retardant to respect ROHS directive. That's done. I know, so now we have to speak about the second step in the process, and now we are working on what we call DRENA+, the plastic fraction with a density over 108. The target is to separate the flame retardant plastics from this mixture of technical plastics. So we do it in two ways. First, we are working with the University of Liège to adapt the prototype pre-kit they use to separate the metals and adapting the lips they have on the pilot to separate the plastics. They do data acquisition, signal processing, and also we have a large data we're done with XRF portable analyzer. And in the same time, we do the benchmarking to another technology that is called XRF sorting technology by RedWave that we have done. So the target here is to enrich, to concentrate all the flame retardant in one fraction. Those flame retardant plastics are the input material of the step 3. What we do in the step 3 is that we will crack, because I told you that we have by Comet a technology to produce char, so carbon black ashes from organic waste, from non-recyclable plastics, and we produce also in the same time char, gas, and liquid fuels, liquid oil. We use the technology to crack those flame retardant to recover the char. This char is concentrating the trioxide antimony. So as you can see on the picture, we have already done pilot test, pyrolysis pilot test on site, and we have produced 300 kilo of char containing around 12 kilo of antimony metals. So this process is interesting because we concentrate roughly at between 94 to 99 during our last test. The char concentrate those antimony. So it means that it's a good way to recover, to concentrate this antimony. And on the second hand, University of Liège started to analyze, characterize this char coming from Comet, and they identified an oxidative hydrometallurgical route to produce and purify antimony trioxide in collaboration with CAMPINE. And CAMPINE also is suggested and is studying another route, a direct route. It means that we could use this char directly as a reducing agent in the process and directly to recover this char in the process to purify and produce the antimony. The last point is the validation, production, and testing. It means that all the plastics and the antimony will be validated and we will produce and test in real industrial and commercial products. For example, I give you here the first result of STELLANTIS, where we can show that work on the FPP compounds and they produce for the both sector, also automotive and electronic appliance sectors. They confirm that they can reach the targets of the sectors, but also they confirm that we are above the 40% of substitution of virgin plastics in their compounds. So the job is already done on FPP and they are working now on the ABS to reach this target. And the next step is coming soon this year. We supply STELLANTIS with not anymore samples, but now with tonnage of ABS and PS when they are to start the production of compounds that will be injected and used by Stellantis. Of course, I will not read the slides, but we are in line with the policy of the Europe, of course, because we respect and we are in charge of several directives. But I would like mainly focus on one. It's not in the slide, but because you can hear a lot of the Circular Plastic Alliance. The objective of the Europe is to use 10 million tons of recycled plastics in the horizon of 2025. So we are a small part of this topics, this target of the Europe to propose recycled material usable in the circularity plastics. Thank you. And I would like to see next time, but in Belgium, on our side to show what we are able to do. Thank you.
Thank you very much, Hervé, for this great presentation, great introduction to our LIFE PlasPLUS project. We'll now move to the second presentation, which will be presented by Charlotte Delvaux of Plastics Europe. And Mrs. Delvaux will be presenting on EU plastic market, a global vision with a focus on automotive and electronic equipment sectors. Charlotte, the floor is yours.
Many thanks. Thanks for inviting me. So I will share my screen now. Please let me know if you see my screen in full. Est-ce que vous voyez ma présentation en full screen?
Not yet. Non, pas encore.
Should be the case. Do you see my presentation?
Yes.
Right. All right. I hope you see it in full screen. It seems that I'm struggling a bit with Zoom today. So many thanks for inviting me today, and I'm happy to be able to present you some key figures that we have at Plastics Europe to set a bit the scene for today's event. So I will. Do you see the slides moving or not?
Yes, it moves.
Slides are moving.
Yeah, okay, good. All right. So at Plastics Europe, we have some publications I'm working on. So I'm the Plastics Europe project manager for Facts and Figures. You may be aware that we have annual publication that we call Plastic the Facts. If you don't, I invite you to visit our website. So here on the screen, you have our last figures that we have published with just before the Christmas break. And we give here some insights on the world and the European plastic production. This is only for, related to virgin. For the moment, our data sets are limited to virgin plastics, at least for those slides I'm showing now. So we can see that in 2020, we have seen a slight decrease in the production of plastics, virgin plastics globally, and also in Europe. So this is also due to the COVID crisis. It has not helped, of course. We can see on the right side that Europe is still has a share of 15% of the global plastic production. I will go on the next slide, where you see actually we have a survey to our members regarding the converters demand in terms of virgin plastics again. And we here present in our Plastic the Facts the distribution between the different segments of the market and the different polymers. So you can see here on this slide that the automotive is still in 2020 has almost 5% of the market share for the converters plastic demand. And then in terms of electrical and electronics applications, then it comes to almost 6%. So you will perhaps ask me whether I can give you the breakdown per type of polymer. So in the past, we didn't give that information, so the data behind the bubbles that you can see here, but as of 2020, we do. So if you are interested in that, you can always contact Plastics Europe. So these were for 2020, but for the year 2018, we have conducted a circular economy study, and you can see here one of the main chart of this study. It is also available on our website, and we are in the process of having a new one for 2020 data. So I'm sorry, but I cannot share the latest data because they're not yet public. We are working on this, but at least this gives you kind of the big picture of some best estimations regarding the plastic circular economy. So you can see on the left side of the chart that in 2018, about 56 million tons of plastics were produced in Europe, but this also includes, so it includes virgin plastics, but also pre-consumer plastic, recycled plastics, sorry. And we had a consumption of about 55 million tons, but this then includes virgin, pre-consumer, and post-consumer recycled plastics, a consumption of 55.4 million tons, and then a waste collection of about 29. The difference between the tonnage of the consumption and the waste collected is also due to the use phase, obviously. For example, a car, you don't buy it unless you have a problem. The year one, and you don't throw it to the trash the same year. So obviously there is a time frame within where you use this item. So in 2018, we had still a landfill estimated to 7 million tons. Then energy recovery about 12 million tons. And we have estimated a 9.4 million tons of plastics waste sent to recycling. It's important to precise this. It's sent to recycling. There is a part that has been exported for recycling in third countries, and 7.5 million tons is estimated to be sent to European recycling plants to produce about 4.9 million tons of recycled plastics, so post-consumer recycled plastics. But in terms of waste, in 2018, we estimate that the biggest part is coming from the packaging applications, and the part coming from electrical and electronics is estimated to about 6%, and for the automotive about 5%. In terms of the way the waste is being collected, we estimate that from the 29 million tons that were collected in 2018, that about 48% were collected via separate waste collection streams. And this, as you can see on the slide, is then producing more, creating more recycling than if you had done it via mixed waste collection. So the plastic waste recycling rates are almost 10 times higher when the waste is separately collected. That's what our study gives us as information. Here on this slide, and you can retrieve that all in our publication online, is that actually from the 4.9 million tons of output of recycled plastics from European recycling plants, we estimate that about 4 million tons of recycled plastics were used in new products in the EU in 2018. So, and from those 4 million tons, then the majority was used in new building and construction applications. So that's the biggest part. The second part is packaging. But then when it comes to automotive, it's 3%, and electrical and electronics, only 2%. I've also given here you some examples. It's a non-exhaustive list of examples where recycled plastics are used. So this is related to the building and construction applications. That's the biggest area where the recycled plastics are used. Then these are examples of packaging products applications, and then here this is for automotive, electrical and electronics, and then other types of products that are also using recycled plastics. Then here for your information, then examples of applications in the agriculture and gardening sector. So now when we compare the use of virgin plastics and post-consumer recycled plastics in the different applications, we see that agriculture, a small sector, a smaller sector than the others, but in proportion, it's using more recycled plastics. As regards electrical and electronics, it's 2% of recycled plastics use versus the rest, and then also the same for automotive. So these are relatively low shares of recycled plastics use, at least for 2018. Then coming back to more recent numbers that we have, published in our Plastic the Facts. These are 2020 data, but these are preliminary data before we publish our new circular economy study. So we can see here that for 2020, we had a small increase of collected waste, post-consumer plastic collected waste. So we arrive here at 29.5 million tons. And from that, we have about 35% of recycling. So here we mean sent to recycling again. We still have 42% of plastic waste being sent to energy recovery, and then almost 24% sent to landfill. The export of plastic waste to third countries has also decreased by 16%. These are our estimations, and here we have the evolution. I show you here the evolution since 2006 to 2020 in terms of waste treatment. So we see now that still the first option, waste treatment option is energy recovery, unfortunately, and then comes recycling, and then landfill. Voilà. So I've been requested also to present a bit our vision for the future. I'll be brief here because I'm not part of the advocacy team within Plastics Europe, but I'm happy to take any question on that if you have. So what I wanted to say is that Plastics Europe is obviously fully committed to support the EU Green Deal's ambitions, and also is taking an active role in the Circular Plastic Alliance of the EU Commission. We see obviously from the numbers that we have from our estimations in our various data sets that we need, and that's not a secret, we need to accelerate the circular economy of plastics. And our members, so plastics manufacturers in Europe, have already started the journey with their value chain partners. So they're working in different aspects, but here are some aspects that I wanted to highlight. So they're active in manufacturing products enabling reuse, repairability, and improving recycling. They also are working on increasing sorting and recycling capacities. It's key to improve recyclates quality and increase the recycling output quantity to reach our targets of the CPA, but also from the Packaging and Packaging Waste Directive. So that's for the packaging sector anyway, and also they're working towards fostering the uptake of recycled plastics into new products. So what I wanted to say here when I talk about recycling capacities, I wanted to make clear that chemical recycling is not the only show in town. Our members are actively working on this, but chemical recycling is not the only technology, obviously, and our members are highly collaborating on also the mechanical recycling technologies, because for the moment, from our estimations, obviously the main quantities are coming for the moment from mechanical recycling. Chemical recycling, we see it as a complementary possibility for waste treatment, and our members have announce some investments. So you may have seen that our members have announced 2.6 billion euros in 2025 and 7.2 billion euros in 2030. And then I would also like to stress that we are contributing to foster the uptake of recycled plastics into new products, but this is more related to packaging. But in the packaging, plastic packaging, we are calling as Plastics Europe for a target of 30% of plastic, recycled plastics in packaging by 2030. I've put here for your information a link to our members' case studies. So there are various case studies, but also collaborations, like I said, to increase sorting capacities and recycling capacities. So perhaps as a last word, I wanted to say that we would like to be at Plastic Europe a catalyst of change and collaborate with our value chain partners to reach common industry targets with openness and respect for all our value chain partners. Voilà, and perhaps something I've forgot to say, and I don't have a slide for this, but as you mentioned, Hervé, the CPA, so I just wanted to highlight as well that Plastics Europe is part of Polyrec. Polyrec is an industry association, and I think obviously perhaps Patrick, who will be the following speaker, will talk about that. I don't know, so PRE is also part of it, as many other European value chain partners. It's an association of associations that is offering a tool to record recycling tonnages and the use of recycled plastics into new applications by converters. And so Polyrec has applied to the CPA to become one of the official data collector to be able to monitor the progress towards the 10 million tons target of the CPA. Voilà. I hope this was all clear. I will stop sharing my screen and happy to take some questions.
Thank you very much, Charlotte. That was really a nice overview of the plastic sector, and especially in Europe, and very informative. Yeah, we are a bit ahead of schedule.
Sorry, I was too short.
No, that's okay. You are quite good on time. So we got at least 10 minutes. We've encouraged people to ask questions through the chat, or they can raise their hands. And I don't see questions now, but in the meantime, I have one for you, if I may, because I saw in some very encouraging numbers in your presentation, notably in your slides. I saw that plastic waste recycling rates are 10 times higher when collected separately compared with mixed collection schemes. So this is very much in line with the strengthening of the circular economy, and I think everything that you're pushing for and fostering. And how do you see that trend evolving? And what else can we all do to improve this? Because there's, I think that was about 53% of the streams that were recycled at 10% higher, but there's still a 47% that needs to be improved. So what can we do collectively?
Good question. I think, well, these are numbers for Europe, but perhaps Patrick can also help us here to have better insights on how to to increase those rates. But I think, and Patrick, let me know if you disagree, but I think sorting, selective sorting is key. There may be also some improvements to be made to recover plastics that are now sent to landfill and to energy recovery. There are certainly some streams that could be recycled and that are not for the moment. So I think, like I said, we need to accelerate the pace and to improve our sorting and recycling. Yeah, so perhaps Patrick, if you want to compliment on this, yeah.
Well, you said most of it already quite wonderfully. Well, what can we collectively do? Well, as individuals, we can take care to deposit our waste in the proper bins. So don't put your hairdryer into the residuals. Bring it to a specific point where it is collected and sent for recycling. But of course, individual responsibility only carries so much. We all know people around us that will probably not listen to this. So indeed, improvements in sorting technologies are vital to achieve all of the targets. Thanks.
Seems quite simple and very general, but I think this is the answer. Yeah.
Yeah, no, but I mean, it's quite simple, but it's a good answer in that I imagine that those plastic waste with the high recycling rates are, I would imagine, PET bottles or things that are easy to be kept as pure plastic stream, as opposed to our plastic at LIFE PlasPLUS, which are inherently mixed with other things, with cars, with WEEE. It would be harder to have clean plastic streams coming from more complex material, I would say, you know, and this is hard to overcome unless you take your own vacuum cleaner and start disassemble it at home and you put the plastic parts of the vacuum cleaner in you know, those hard plastics that they have in the receipt parks and stuff like that. But yeah, it's asking for a lot. I mean, we're starting to slide into the discussion on design for recycling and instruction for dismantling, which I haven't seen yet in common household appliances, unfortunately. I see that Hervé and Jérôme are there. I don't know if you guys see if there's any more questions for Charlotte or any specific topics that you would like to discuss, maybe in the chat. I don't know if there's any other topics. Okay.
If people want to reach out to me bilaterally, that's also fine.
Yeah. Okay. Well, thank you very much. Anyways, we'll be together with for the panel later on. So if anybody comes up with a question or an idea, we can move on from there. Oh, I see Jérôme here is saying any question, don't be shy. But like I say, we'll relay those. Well, thank you again very much, Charlotte, for this. And I see that Patrick de Kort is online. So if it's okay with you, we can possibly move with your presentation. Is that would that be okay?
Philippe, there is a question in the chat.
There's a question. There's a question.
From Benoit.
We have 7 minutes for that question. Please. Okay.
Benoit.
Should I relay?
I have to activate the sound. Benoit.
I think Benoit will ask his question verbally. Is that correct? Benoit, if you're there and you can unmute.
You can hear me or not? Philippe?
I can hear Jérôme, but I cannot hear Benoit.
Yeah,
Benoit, on vous entend, Benoit.
Okay. Okay. Perfect. Thank you. So I am Benoit from the CTP, Centre Terre et Pierre at Tournai. First of all, I want to thank you for the presentation and congratulate also the partners of this project, since it looks very interesting to see the situation of plastics in Europe. I have just a small question for Hervé and the presentation. You presented the project, the LIFE PlasPLUS project. In this project, did you work on the light shredded residue, because I've seen in your presentation a lot of rigid plastics, which should be, I think, heavy, but is there, would say, research done on the fluff, the light shredded residue, or it was not the topic of the project? I don't know.
So, by Comet, we treat both light fraction and heavy fraction. You have to know that the quality of the light fraction and the heavy fraction is depending on the power of the air suction that you have in your shredder. So you can have rigid plastics in both fraction, also in the light and in heavies, of course. So by Comet, we have the tool process on the heavies and the shredders. So we recover the plastics also from the light, and we extract all the valuable plastics from the light, and we create what we call a fluff, the very light material with non-recyclable material, complicated like foam, textiles mixed together with fibers of wood and so on, and textile. That's the real fluff, and this fluff is going to the Phoenix project, the Phoenix process. That means the catalytic cracking to produce oil and electricity. So it's coming really from the two qualities, heavies and light fraction.
Okay, thank you. It's just my curiosity. Thank you very much, Hervé.
Welcome.
Thank you, Philippe.
I don't know if there's any more questions. If there are not any more, let's move on. And if there are any, maybe we can leave that for the panel. So without further ado, I would like to present Mr. Patrick de Kort of Plastics Recyclers Europe, who will be presenting on plastic recycling in Europe, and specifically a focus on plastics from end-of-life vehicles and waste electronic equipment. Thank you very much, Patrick. The floor is yours.
Right. Thank you very much. I have to admit that quite a bit of the things that I'm going to be saying Hervé already stole from me. But I'll try to give a little bit more broad perspective, a helicopter view, if you will, from the sector in which companies like Comet Traitements are placed. We refer to them as technical plastic recyclers. These are recyclers that are basically dealing with the plastics from ELV and WEEE sources. So first, a small word about Plastic Recyclers Europe. It is a European level trade association of the companies that do plastic recycling. We have now more than 150 member companies and organizations. This includes, of course, plastic recyclers, but also machine manufacturers, additive suppliers, and some other national associations and so on. It's a young association, which is also reflective of the youth of the plastic recycling industry as a whole. I think in the 90s we started with actually 10 or 12 companies, and now 25 years later we are at this state and have grown in tandem with the industry. We're organized into 6 plastic waste stream focused working groups, mainly revolving around different kinds of polymers. So we have LEPE, making films, PP, PO, pots, tubs and trays, PVC, large section for building and construction, PET, of course, the bottles and the trays, and the technical plastics working group. And we aim to be the voice of plastic recyclers in Europe. So let's see how well we achieve that. Now, this is a very busy slide, and that is because they are going to be distributed afterwards. I'll try to talk you through it. Don't spend too much time reading it. But just to echo Hervé, the input for plastic recycling specialized in technical plastics is very heterogeneous. All sorts of polymers, all sorts of impurities in the form of wood, rubber, metals, minerals, foams, wood, cables, etc. Now, this composition also differs a little bit based on the origin of the material. In the table, you have different kinds of sub-specifications within the WEEE and ELV shreds. So, for example, you have temperature exchange equipment, that's fridges, relatively clean stream, lots of PS, and then you have small equipment, a little bit more heterogeneous and a little bit more of brominated flame retardants as well. Because that's another part that these brave recyclers are having to surmount, and that is to deal with legacy substances. Namely, indeed, these brominated flame retardants, some of which are currently still on the market, the newer ones, the not regulated ones, the safer ones. But our members have to deal with the older ones, the polybrominated diphenyl ethers, which have been identified as POP, persistent organic pollutants. They're banned in virgin material, and they may not be recovered, and they need to be destroyed. So then you could ask yourself, okay, well, how do these recyclers exist? Well, they do density separation. And if you add a brominated flame retardant up into a functional level into a piece of plastic, then that piece of plastic will get a greater density. Here you have a little bit of the legal framework. So there's a limit of 1000 ppm for the PBDs. There's a sum total above which the waste becomes pulp waste. Pulp waste needs to be destroyed, but you are allowed to make concentrates, and that is exactly what the recycler does. So here you see the input, and then if you then look to the waste, obviously, because you're creating a product fraction which is almost free of the PBDs, the concentrate is in the waste. And through these activities, the plastic recyclers dealing with this material, they not only contribute to a circular economy, but actually they also contribute to a toxic-free environment, which is one of the other big policy topics of the European Commission and the EU as a whole. Now, one of the main problems with this process can be found here. If you do all of this with normal shredder light fraction, you create product fractions which are good and well, but you also create large amounts of waste residuals. Now, these waste residuals will contain pieces of other polymers with higher densities. For example, polycarbonate is a density greater than 1.1. And there will be flakes of lighter plastics with brominated flame retardants, but there will also be heavier polymers, which have been made even more heavy through the use of flame retardants. So it's a difficult thing there. Now, if you look to the structure of the industry as from the helicopter view, there's still a lot of complexity. And in doing market research, it is not easy to have this level of complexity. You can't simply go to a website and see that someone is dealing with ELV plastics and simply assume, okay, well, then the capacity that they have listed on their websites is a capacity that we need to count, because there are, for example, companies that simply take this thermic fraction and do electrostatic sorting. And then you would have double counting because it has already passed our calculation point. And all of the boxes here in green are things that can be the result of the recycling value chain. You can have polyolefin regrinds, you can have polyolefin compounds, you can have ABS regrinds, ABS regrinds separated, but you can also have styrenic blend regrinds being used in the conventional compounding and converting value chains. Now, the way we deal with this complexity is through simplification. When we do market research, we only look at how much polyolefin fraction is being produced and how much styrenic fraction is being produced. And we identify those companies that actually deal with this kind of separation step. Because in subsequent steps, yes, there is still residual waste, but not the absurd numbers that you get when you're in the earlier steps in the process. Now, we did this, and so far we have been able to identify 17 plants in Europe which have the capacity and the competence to deal with this specific, very difficult plastic waste stream. In total, the capacity was 442 kilotons, so it's not a minor industry. And the sector produced an output of useful plastics of 192 kilotons. Now, obviously data is good, but we also need a little bit of interpretation. So we also did telephone interviews and in-person interviews with some of the key players. And we actually found certain things which were relatively shocking to us, relatively shocking from our ivory tower in Brussels. For example, not all WEEE, and particularly not all ELV plastics, is sent to recycling facilities. Quite a lot is going directly to energy recovery. Why was this shocking to us from our ivory tower in Brussels? Well, there's this thing called the WEEE directive and the ELV directive, which states that this stuff has to go to recycling facilities. So, yeah, that is a practice that should actually not exist if you look to the paper that was drawn up in Brussels. What we also see is that export of certain qualities of WEEE and ELV plastics to non-EU countries occurs with possibly poor recycling practices. To give you a practical example, WEEE treatment centers, they take in TVs, and you have these old CRT TVs where you have the cathode ray tube and there's a little bit of mercury inside. Now, in the WEEE directive, it's specified that these WEEE treatment centers need to have a procedure to remove this mercury safely and send it to a specific location for other waste treatment options. Because they have to take that mercury cathode ray tube out, they have to take off the back of the TVs. And so there are large volumes of TV back casings out there. If you send them to proper recycling facilities in Europe, you will probably get a recycling rate of 40–50%, because all of the back casings or all of the parts of back casings with brominated flame retardants are separated and sent for destruction. If, however, you send it to a company outside of the EU, I mean, these back casings, they're all styrenics, there's technically, from a technical perspective, physical mechanical properties perspective, no reason why you shouldn't be able to blend these together to create a new recyclate for new products. Unfortunately, of course, that creates problems. Because then you are not removing the pops, you are simply diluting them. And diluted, they become a bit greater problem for the European waste management infrastructure, which is currently still relying in large part on density separation. Another observation that we had is that there was quite a bit of trouble getting this kind of plastic waste across borders. Some member states said, well, yeah, if you do not make any cuts in density at the waste treatment center or at the ELV treatment center, then it's pop waste. And whilst officially pop waste under the European legislation is not hazardous waste, some member states have decided it is. Yes, welcome to the unified Europe. And when shipping that across borders, you have to go through notification procedures and all sorts of shebangs and loopholes. So what did many of these treatment centers do? The treatment centers are the places where plastic waste is generated. They created a very simple pre-floating facility. Nothing fancy. Relatively simple technology that simply makes a cut at 1.1 gram per centimeter cube. The lighter fraction from this contains the polyolefins and styrenics and should be almost free of brominated flame retardants and thus can be shipped across Europe wherever. And even some of these centers were exporting to outside Europe. And then you have a heavier fraction, which is supposed to go to incineration for destruction of these very nasty flame retardants. Now, that's a trend that we observed. We're not necessarily happy about that, but more on that later. I was also asked to give you some challenges and opportunities. Well, there are obvious ones. The fact that this kind of plastic waste, especially from ELV, is being sent to incineration. I mean, that's a waste, huh? That's terrible. And so we encourage all these member states to take action on that, and as well the EPR systems behind these kinds of waste streams. Then we also see that there is export of this material. Not necessarily happy about that because, well, this is raw material that could have been recycled within Europe now, isn't it? Now, there are provisions right now in the waste shipment regulation proposal from the European Commission to make it more difficult to send waste abroad by requiring third-party certification of non-EU facilities receiving waste. We hope that that will help, but we will not. This is not a ban, and well, we're also not calling for a strict ban, but at the very least, we hope that this certification system will prevent these very poor waste management practices. Then another challenge, and to be honest, when I was making these slides, I was a little bit more pessimistic about the world than after seeing Hervé's presentation, because Comet seems to be quite well advanced on this point. But most of the recyclers, they're still sending this more heavy fraction for destruction. There is a large fraction of PC and PCABS alloy in this fraction, some of which will be containing brominated flame retardants, and others will, another fraction will not be. There are companies working on technologies to first separate this PC and PCABS and then do another density separation step to obtain a fraction of PCABS that is almost free of these brominated flame retardants. And there are more such initiatives, and all of this should result in a greater concentration of the brominated flame retardants and more liberation of non-flame retardant material for use in the conventional plastic compounding and converting industry. Now, this is a development that originally I saw a 10-year time frame for to be adopted at scale. Now I'm a little bit more optimistic. Also of note is that if you would do this, then of course you will get a greater concentration of the antimony level. I thought I'd mention that here to aid you on your project. On these pre-floating facilities, we see benefits and we see risks. The benefits are mainly short-term. Short-term, hey, these treatment centers are generating a fraction which will cause less waste at the specific plastic recyclers. Yeah, that sounds fantastic, right? Because waste is something that you have to get rid of and it costs something. So basically, this whole steps transfers a large part of the costs of getting rid of the more heavy fraction to many different WEEE treatment centers and ELV treatment centers. Yeah. We also see a longer term risk because, and this has to do a little bit with lock-in. Because there are relatively few recyclers that are actually doing the separation of the plastics into different kinds of polymers and making something useful and are actually recycling the material. There are many, of these WEEE treatment centers and ELV treatment centers. And if you would have the problem with the recyclers, so the recyclers have to take care of this heavy fraction, then we see a greater opportunity for investment and innovation in that sector, because you have economies of scale. So in general, the industry believes that there is little benefit from simple pre-flow technology being used by WEEE and ELV treatment centers to produce a shippable plastic waste fraction. But that is unfortunately still something that we do see happening more and more, and that is driven by legislation. An unfortunate side effects of waste shipping regulations being so strict as they are. Another thing that we think that is a fantastic thing that we think that could potentially increase the recycling rates for this plastic waste stream even further is solvent dissolution technology. In solvent dissolution technology, you selectively dissolve parts of a waste stream, for example, polymers from non-polymer material, and selectively precipitates other what you dissolved. For example, you could, in theory, dissolve additives first, polymers later, or the other way around. It is being used effectively by PS Loop in Terneuzen, the Netherlands, to separate HBCDD, another brominated flame retardant from polystyrene foam from demolition waste. So we are hopeful for this technology and its ability. Then, yeah, we have to acknowledge here bromine and antimony are also very dear and expensive things. And actually, we can all take a little bit of a pointer from PS Loop, because there they indeed separate the HBCDD, but then they sent that HBCDD across the streets to a colleague, which is having a bromine recovery unit, which basically burns the HBCDD at a very high temperature, destroying it, but recovering the bromine from it for the production of new, safer flame retardants. So, yeah. We see also that the viability of such technologies to recover these materials becomes greater when you get more material that is not flame retardant from the heavy fraction, and that should facilitate the recovery of these valuable molecules. That was it a little bit. I've given you an overview of the trade association, the market as we know it, and some of the challenges and opportunities. And now I would like to ask you if you have any comments or questions or desires to follow up.
Thank you very much, Patrick. That was very nice, and you went a little bit further in the subject, specifically in the terms of technical plastic, which was quite interesting. I have. Can you hear me properly?
Absolutely.
Okay. Good. I know there's probably some questions, but I'd like to ask one to start things. You mentioned that some of these plastics are undergoing incineration and or being shipped outside of Europe legally or illegally. Anyways, they're being diverted from their proper route, which should be recycling. But some of these plastics that we lose basically through incineration or shipping can be quite valuable. Concurrently, we're living in a period of very high inflation, where petroleum-based products are increasing in price. And we have supply chain bottlenecks. You know, we hear of that for some circuits and chips. Aren't we maybe to the point where this incineration or this shipping cannot be abated because of the inflation or supply chain bottlenecks, which render Europe more dependent on the import of such materials?
It's a very good question. Now, firstly, it's the oil price that is driving the inflation, not the other way around.
Well, I would argue that it's Jerome Powell and the monetary printing, but that's another debate
as well. But anyway, yes, indeed, quite a bit of this plastic is valuable.
Yeah, but
the state in which it is when it is coming from a WEEE and ELV treatment center, it's not immediately suitable for reuse. Yeah? That's why we have such lovely companies such as Comet. That mix of things needs to be separated by someone. And it is the recycler's job to create order out of chaos. But a recycler can't do that for free. Yeah? There are processing costs involved in this separation and preparation to create something that is useful in the conventional compounding and converting industries. Yes, on the other hand, I have to admit, it is a good time to be a recycler. Yeah? The price level that is achieved by recyclates is very much dependent on the price level of virgin material, which right now is sky high. Yeah? Demand for recyclate is very good. What we do see then, of course, as a consequence is that recyclers are vying and fighting one another for input material, as they should in the competitive market. Nothing against that, definitely not as a trade association. And also the price levels of waste increasing. The increase in the price level of waste, however, is less than the increase in the price level of the recyclates, as you can imagine. Yes, maybe some of the plastic waste fractions now become more interesting to send to recycling, but it will also depend very strongly on the gate fee that is levied for incineration. Yeah. This ELV is going to incineration. It's not by chance that happens quite a bit in Scandinavia. Gate fees for incineration, 60 euros per ton. And if you have to pay more to send it to recycling, yeah, well, then you have your incentive. Whilst in other regions of the world, where incineration is a lot more expensive, can sometimes go up to 200 euros per ton. Yeah, there you see more and more material being sent to recycling. And of course, indeed, you have to compete with exports.
Okay, thank you very much.
Answer to your question, or do you have a follow-up?
Yeah, no, that's fine. I mean, it's, as always, it's not a simple thing, because obviously, yes, in the end, if I hear you well, you would argue for recyclers to really upgrade their facilities to be able to treat more of that material. But then again, it will depend on how long these prices will stay high, because you have to amortize the installation. So it's a trade-off, you know. So, but I think Hervé had a question, and Hervé's beside me, so you might want to have a question for Patrick.
Yes, and I would like to add light to your presentation. I think you're right, talking about the density contained on 101. And when you talk, yes, but the risk is that in the next year, it will be limited the development on separation on the heavy plastics. You are right, but I think if we come, why is this technology the state of the art currently? Is because there is no other solution industrially profitable and economically viable, because, as you know, black plastics is a big problem to separate it. And so if you want to have good yield of separation, you need to do this process. And you highlight, your presentation highlight also the fact why we have this R&D project, because of course we are quite a good level of to do demonstration of technology to separate ABS, PS, and fill quickly. And on the other hand, the second step of the LIFE PlasPLUS is to face and to suggest a way to recycle the flame retardant plastics. Is the key topics, because it's very complicated. That's why we are in this European project to receive fundings to suggest one solution, because it's very complicated technically and economically. We have to see what will be the result of this project. Thus, we suggest a way of recycling those antimony, and those bromine, but it's very hard stuff. And with the University of Liège, on the other hand, we are also working on this technical plastics, like you talk about PC, ABS, PMMA, and so on. Thus occur topics from local government, from Walloon area. We are also on another project to recycle those technical plastics. That's the future, of course. But now we have to find the right technology and to validate the quality of the material, and the target is, or the goal also is to convince the end user of technical plastic to use those recycling. I think PP, PE, ABS, and PS is a long time story of recycling, but when you are talking about PMMA and PBT, POM, and others, I think post-consumer coming from those technical plastics, what will be the point of view of the end user? Because they are not, I think, those market is not so huge than what we have on the four main plastics that we are recycling. That's important in the future to have a development of this. And I have a question for you, because it's more administrative question, and maybe it's the same question that I saw my colleague asking to have a question is, when we produce recycled material on administrative way, is always a waste. It's a green list, but still a waste. And we would like to know when it will be finished, this situation, and to have a global end of waste status for recycled plastics coming from facilities like ours, like we do. Now we produce high light quality of thermoplastics, high quality of FPP, ABS, and so on, and PP3, but it still have the name of waste. I think it's a pity that we have in this situation. I think Europe should help us to go out of this status of waste. What is the goal of Plastic Recyclers Europe to help us to receive this end of waste status?
Oof, you're not the first one that asked for this. Indeed. Oh my. Many recyclers, especially in the Benelux, they have a bit of a discussion with their competent authority on the status of the recyclates. With companies arguing it's a product, and the authority saying, oh, but did you check whether or not it meets the end of waste criteria defined in the waste framework regulation? Now, most often when that question comes back from an authority, most recyclers, I have to admit, they're not very well prepared. They basically then start reading the waste framework directive and the criteria listed there. And then they call me. And then I tell them, well, look, first of all, yeah, if you want to have this your material identified as a product, then you need to argue that it is in compliant with the 4 criteria. Now, the first 3 are relatively simple. You have to show that there's demand, it meets technical specifications, it has a specific purpose, and then you come to the last one, which is saying that you need to make sure that there is no overall adverse impact on human health or the environment. Okay. Now, you as a recycler might think, well, I'm recycling. Of course, this has a benefit for the environment. Yes, I agree with you. But you're not talking to the people within the government that care about that. No, you're talking to people that care about the toxic-free environments. Yeah. And you need to start demonstrating that there are either no hazardous substances in there, or that hazardous substances are below the legal thresholds in product legislation. And then you come to a problem, because then you have to test for hundreds of substances. Yeah. Now, within PRE, we have developed a tool called PRE 1000s, where we made an index of all of these substances and identify and analyze them whether or not they could be present within recyclates. And then there is even a bit of extra ref analysis and smart calculation behind it to further exclude certain substances. And then you only have to do a few chemical analysis on top of that to get your answer. It is the most cost-effective, most holistic, most complete way to deal with this issue. And it is freely available for any and all recyclers. Hervé, I actually sent you an email about it last year, remember, to set up some training for your personnel on this topic. And I would be very much happy to join you at Comet to take your people through this.
Yeah, that's quite a challenge, and because there's quite a lot of substances. I think at least some of the plastics of LIFE PlasPLUS have passed the ROHS free stage, and I think that's very much on Comet's mind to keep supplying POP-free plastics, but it's sometimes it's difficult. Hervé, I don't know if you have anything to add to this.
Of course, the key is to respect those regulations. That's why in the presentation, I focus directly on the ROHS directive to show that we take care of what that is. Of course, if we want to integrate more and more recycled material, recyclers has to prove that they are working correctly. So it's just to see, maybe to help us to find an easy way to get directly, because we can.
Don't understand me wrong, Hervé. Being WRF compliant is already a big step up. And based on what I've seen from your process and the results from other recyclers, I don't think that there will be a massive problem with hazardous substances in your recyclates. But you need to demonstrate it for the authorities to get your antimony status. Yeah. And we have a method for that, and we'd be happy to teach you.
That will be the next step for us.
Yeah.
To work together on this point. Thank you.
Okay, so I think we're at 10:32, so we're pretty much on time. Very much thank you for this presentation, Patrick, and this discussion as well, and the suggestion to commit. So that's very nice. So now we will move to our next presentation, which will be delivered by one of our.
Coffee, please.
Oh, there's a coffee break here. Oh, sorry.
On fait un petit break d'abord.
Yeah. Oh, no problem. Okay, so we are going to go to a coffee break. Thank you very much for reminding me to give people a chance to go for a coffee. I'm here rolling and motoring through this, but we'll see you then in 15 minutes. Have a break, and we'll happily be back in 15 minutes. Thank you very much.
Thank you.
Now we'll move on with the second part of the morning session, and we'll host one of our partners, Stellantis CRF, with Mr. Gabriele Ciaccio. We'll be talking about thermoplastic recycling, and this will be the view from the automobile industry. So without further ado, Gabriele, the floor is yours. Thank you.
Okay, good morning, thank you. I will start to share my desktop. Are you able to see?
Yes, we see it. Thank you.
Okay. Okay, then good morning to everyone. You are seeing also the slide moving. You see my agenda?
Yes, correct. We see your agenda.
Perfect. Okay, thank you. Then, okay, this is my agenda. I will, there are a few slides regarding the introduction, vehicle application, recycled materials, and then we go to the conclusion. Then we start with an overview of the materials that are composing a vehicle. You can see that the majority obviously is steel, but we have a huge number of different plastic families. The main one are the polypropylene with the 42%, but we have also other families like polyamide and styrolic ones that have a huge percentage. In the last 2 years, we discovered the weaknesses of our European system due to the pandemic and some logistic issue. And we discovered that a lot of production are coming from, and a lot of are coming from outside Europe. And this has have an impact of our production with difficulties to find materials in the market to be used for our production. This is a table, a graph in which we summarize what happened, for example, in Italy last year, where we had several plastic material shortages. You see that the main problem was with polyamide, but we had also problem with styrolic PCABS and polypropylene. And the fact that we will be able in the future to increase the plastic material recycled probably will help us to face more this issue. Another thing that has an impact on the usage of recycled material in the automotive sector is the fact that we have now some changes that probably will come in the next month of years of the legislation that probably will ask to OEM to increase and to declare a certain quantity of plastic material recycled used on each vehicle produced. And also all the OEM, including us, are giving and are a target of recycled material inside the vehicle. At the moment, for our vehicles, we have a target that we are trying to reach of 2% of recycled bio-based polymer in our car. And then we jump to the vehicle application. Here there is a focus on polypropylene and styrolic grades, filled and unfilled, that are used in for vehicle production. We have some potential application here in this table for recycle grades coming from the activity of a PlasPLUS project. You can see that the majority of them regarding polypropylene and PCABS are related to not feasible components due to the fact that using recycled material is not so easy to manage, to maintain stable the color required for that kind of application. And as aesthetic, we have indicated only an application painted. Jumping then to recycled materials, what is the status inside our company? Currently, we are using recycled polypropylene and PCABS for some application. As I said, and you can see from the picture, are not aesthetic because we have some aerodynamic shields. We have some components inside the dashboard. And in the last month, due to this huge push to increase this huge internal push to increase the quantity of recycled materials inside our vehicle, we characterized a huge number of grades and compounds, more than 170. And this brought us to create new standards for this kind of compounds. And in particular, we focus on the main families that you saw in the first chart of this presentation. If you remember, the quantity, the main families of plastic used in our vehicle are the polypropylene with about the 40%, the polyamide with about the 14%, and the PCABS with about the 7%. And then we focus on this free family, and we create these free standards. We've indicated the properties that must be reached by these new compounds, and also all the compounds that we tested and have been able to fulfill the requirements. These huge number of compounds will be used and are used currently for the new developments to be able to reach the target that I showed you before of the 2%. And I can say also that this target probably will increase in the next month or years to become more high. Yeah, as you can see, there are a picture of and the focus on the two standards regarding polypropylene and PCABS compounds that, as you see, has been created last year, but has had updates also each month, because each month we are introducing new compounds inside them. And then now, as you know, we are, from the point of view of Stellantis, we are a young company. And now as a new company, we are creating a global list of approved green materials to be used for each new developments. Then putting together the experience of the companies that have been merged inside Stellantis. And currently we can say that we have more than 400 green materials are approved and are ready to be used for the new developments. And I would like to say that the majority of these grades approved are post-industrial polypropylene, And then because obviously is to create a compound with properties closer to the virgin grade is easier using a post-industrial grade. And then the polypropylene that we are developing inside the PlasPLUS project could be a good opportunity to introduce a polypropylene coming from post-consumer recycled material. And also from the point of view of the PCABS, the majority of the grades that we approved and we have in our list are grades with the polycarbonate recycle inside. And we have not, I can say that I do not remember any grades with ABS or a fraction of the ABS recycle. And then this project give us an opportunity to be able to test and to understand if how and to introduce an ABS fraction in the PCABS compounds to be able to increase the green content also of this kind of material, and to be able in this way to increase the final quantity of recycled material in the final vehicle. And then I'm jumping to the conclusion of my presentation. And the challenges that we see in the future, the shortage that I explained before due to the logistic difficulties, shipping cost increase, and the volume decrease of the material exported from Asia because the huge growth of Asian market was also a reason to the difficulties to find some type of products due to the fact that they have been used for the local production. The logistic difficulties was, as I explained before, due to the pandemic, but and that bring also to a big cost increase of the shipping. And we have to work to avoid this kind of problem in the future. And one of the possibility is to increase the recycle fraction of our plastic waste. In this case, we will be able also to decrease the necessity of virgin grades that are not produced all internally in the European market. And the other big challenge is sustainability. All companies are called to be more sustainable, and this is something that is required by legislation, but is also an internal target that each company is giving to ourselves, and this will push companies to search for new potential application of plastic recycled grades. And then we think that with the activity of the PlasPLUS project, we will be able to bring and in production post-consumer recycled polypropylene and ABS, and that will help us to increase the quantity of post-consumer recycled plastics in our vehicles that, as I said before, currently the the fraction of the recycled plastic material used are mainly coming from post-industrial scraps. And that's all from my side.
Thank you, Gabriele. That's very nice. Very happy to see, in fact, that the LIFE PlasPLUS project is helping to decrease the dependency on these weakened supply chains that we face and that you face as well. So it's nice that you bring this up. We have a little bit of time, and I know there was a question from the floor from Mr. Frédéric Denio, I believe, and Peñu. So maybe Frédéric, you can ask your question directly to Gabriele.
Yeah, thanks. Thanks for giving me the floor. I had a question. Do you hear me?
Yes. Yes.
Yeah, okay. Gabriele, I had a question. I'm interested in knowing whether you have, for instance, discussion with your tier suppliers in order to push them to insert recycled plastics in components they use for the casings or whatever the use in the battery you will use for e-traction. You know, there are some part of plastics that can be used in this, and recycling plastic is, to my understanding, possible. So the question is, do you push them to do so or not?
I can say that currently we are pushing the application of recycled materials on, I can say, the standard that's most known application. Okay, then I'm speaking about body application, underbody, chassis application. About battery, I have to say that, as you know, we are increasing the number of electric vehicles in the market, but at the moment, due to the fact that a new technology is, I know that is not new, but is not well consolidated as combustion engine. I think that I'm not sure that we are ready to start to put recycled plastic grades inside the battery, because at the moment we are facing on other aspect of this kind of application, because the battery has some new needs and some new requirements regarding the safety that we are trying to address with specific tests and specific requirements. And then I think that when all these aspects will be fixed, or at least we have been able to better identify, we will be ready to introduce plastic recycled materials inside the battery.
Okay, for the future then. Okay, maybe. Okay, thanks.
No, for sure we will put. We will have to put something there, because the battery will be now I don't remember exactly the number, but the weight of a battery is on the whole weight of the car is significant. Then it will be necessary also to work on that.
Mm-hmm.
I do not see something in the next month, okay? But I think that in the coming years we will start also to propose something for this kind of application.
Okay. Thank you, Gabriele.
You're welcome.
I don't know if there's any other questions.
I have another question.
Oh,
I'm Karen.
please,
Hello,
please.
hello. Good morning. I'm
Very
Karen
good.
Janssens from CAMPINE, and I'm a colleague of Hilde Govaerts, who is also part of the project of LIFE PlasPLUS. And I was wondering, Mr. Ciaccio, if if the polypropylene or the PCABS recycled materials that you are using for the body, are they flame retardant in the sense that, for instance, the recycled antimony trioxide that is coming out of this project could also play a role in the recycling content of this new compounds that you are generating?
Okay, the compound that we use for the interiors for sure have a need be flame retardant, and yes, we have this requirement for the grades that we use for the interior of the vehicle. Then the answer is yes.
Yeah. Okay, thank you very much.
You're welcome.
We have a question from Patrick de Kort for Gabriele.
Yeah. So one of the things that's I quite frequently hear from my members is, oh, we don't supply into the automotive market because they have such high standards in terms of physical mechanical properties that recycled material can't possibly meet this. Okay. Some of these recyclers are quite pessimistic, I have to tell you. But one of the things that these recyclers then subsequently say is that, well, maybe the specifications for automotive parts have been over-engineered and actually need not be so high. What is your view on this, and would you be willing to accept some compromises in terms of physical mechanical properties, if that would allow a greater recycled use of recycled material?
This is a good question. Okay, as I said, we created new standard to collect these recycled grades of plastic materials, and I can say that we have been more elastic regarding mechanical properties for this kind of grades compared to the virgin one. Not too much, okay, because obviously we have to grant the final performance on the vehicle, but I can say that we changed something, okay, and as I explained, we have characterized and put in the standard more than 170 grades. Then I can say that it's feasible, okay. And there are, as I said, not the majority are post-industrial, and then obviously if post-industrial is easier to reach some performances, but there are also some post-consumer grades. Then I can say that is feasible.
Well, then thank you very much on behalf of the entire recycling industry for this.
You're welcome.
Yeah, thank you very much for this fruitful exchange. I think we'll have a question from Hervé. Please go ahead.
Gabriele, so if I understood well, I think a good point that I heard from you is that you create a standard of materials. So you create a new standard for post-consumer plastics. Does it mean that in the future, when you will create new components, new vehicles, you will be able to directly do the dimensioning, the engineering of the part directly with recycled material, instead of what we saw now, most of the time, is that recycled material should replace the virgin plastics and has to be just a lower price. So that means that in the future you will design new vehicles, new parts directly with the standard of recycled material. It's a new kind of, you create a new normalization.
Correct.
This philosophy that you are working?
Yeah, is this is the philosophy behind the creation of the standard, is what we are doing. We are doing this activity currently. Then in the project that are coming, we are doing that. We are also starting to perform also characterization for the virtual analysis, and then we are giving data to our virtual analysis team to perform also simulation with this material. And then, yes, this is what we are doing because without this new standard, without this data for the virtual analysis, it is obviously not feasible to create a project able to fulfill the final requirement of a complete vehicle in the real life. Okay, then yes, the answer is yes, is that we are doing right now.
Okay, that's a good news, and it's important. So I think this way could be the right circularity, because you will directly take account about the reachable properties that we can do with recycled material. And I'm happy also to read that you would like to integrate 2% of green material. It's very also a good point to you will push the designer to help to integrate more material. But if it's recycled material, is very good. But just to take care about the bio-based material, because for this material, the recyclability, and sometimes it could be very complicated to recycle it. It's more new material in the mixture, so it could be complicated to sort it and to reintegrate in the circularity.
Consider that most of the time for bio-based, we mean that the source of is not petroleum, but is an oil coming from bio. Then at the end, the final polymer is the same, okay? But then you will have the same polypropylene, but instead of coming from naphtha, is coming from I don't know, some oil, some scrap of oil coming from the kitchens or something like that. Okay,
that's good. Perfect.
And then because the ones that for example, PHA is not so easy usable inside the vehicle due to the thermic performances that the requirements that we have. Then it's not so easy to use a biopolymer. Okay, when I say biosource, I mean that is most of the time is completely the same polymer. Okay, what you can see in the future is usage of natural filler. Okay, because natural filler are increasing in application, like wood scraps, something like that. Not only but well, I think a lot of OEM are working on this topic, and there are several articles and pictures in internet regarding application of natural fillers.
Yes, but the point of natural fillers, sometimes when you do the recycling, it could create a smell in the recycled material. And
is a good point. That yeah, it's a good point. It's something that
yes, but after to come back in the car.
Yeah,
that's a good question to see. We can we could recycle. We can recycle the PP with 10% of natural fibers, but when you put it in the extruder machine, after that you have more smell of wood or the so it's important to think about that. And
sure, this is a good point.
Maybe to add to that, on bio-based polymers, you can have bio-based PT, for example, which acts, smells, and behaves exactly the same way as petrol-based PT. And then you can have the bio-based polymers such as PLA, which are simply different polymers. But if you would use bio-based polymers, yeah, okay, why not? But when you're talking indeed about these wood fibers, it's not as bad as glass fiber field material, but yeah.
Hello, good afternoon. Can I have a question? I will start my video. This is Rob Tol from Automotive Europe R&D. Can you hear me?
We hear you, yes.
Okay, so yeah, thank you for the presentation. I think we share quite a lot of the same challenges. It's quite recognizable, so thank you for that. I just have a practical question. As you've all been looking at targets for recycled, and as you've been setting as well, but actually, how do you manage, or do you have a good system to trace actually the amount of recycled or recycled content on the vehicles? Because this is something that I think we all struggle with a bit, like what is the supply chain using, and if there is a good, let's say, platform and way of doing that. Of course, it's depending on our internal systems, but I was just wondering how is that being considered in Stellantis?
Okay, this is a good point. This is a good point. I can say that that is a point on which we are working on the traceability of this kind of material. Currently, there is a team that is dedicated to do this job, and is an ongoing working. I have not definitive answer today, okay? But it's something you put, you touch a good point, because it is an important point. We put and we ask, and also on the internal production, we are sure about the traceability of the incoming material. We ask the same to supplier, and we have to understand in the future if we can have something better to trace this kind of material used in the vehicle. I can say that as you know, all the car maker has the AMDS system, inside which there is the request to each component supplier to indicate the percentage of recycled material inside the component. This is a potential solution to address this kind of problem. And it's something that we are discussing internally. I have not, but right now the final decision. But it's something that on which we are working. Yeah, I completely agree with.
Yes, currently a lot of manual work is needed, I think. Still well pending, so yeah, okay, thank you very much.
You're welcome.
I think that's probably it. Gabriele, you've suffered a lot of questions, but you've generated a very constructive discussion, and we thank you very much for this, and we thank you for your partnership as well. So thanks for that. You'll be around for the panel anyways if there's further discussions to be had on certain subjects. So now,
thank you to you. Bye.
Thank you very much, Gabriele. I would like to welcome our next presenter, which is also a partner in our LIFE PlasPLUS project, Mrs. Hilde Govaerts of CAMPINE, who will be talking about the antimony value chain. So Hilde, the floor is yours. Hilde, you have to unmute, I think. I think you're still muted.
Sorry, I'm still preparing.
Oh, okay. Sorry, I caught you off guard a little bit. Sorry about that.
Okay. Do you see my PowerPoints or?
Yes, we see very well.
Okay, very welcome, everybody. I want to give you a view on the antimony value chain, because that's why we are partnering in the LIFE PlasPLUS project. I will present you who is CAMPINE, what are the main uses of the antimony, of course, focusing on the flame retardancy applications. And then I will give you a view on the importance of the recycling of flame retardant plastics in the total value chain of antimony. First of all, we are a company in Belgium, and we have two different divisions. The first division is the CAMPINE specialty chemicals, where we produce 12,000 tons of antimony trioxide. Currently, most of this antimony is produced out of virgin antimony metal coming from China, but already we have already a capacity of 10% of recycled antimony, which I will explain you later. 6,500 tons of master batches. They are mainly intended to use in flame retardancy applications, but also other applications with high filled plastics are possible. The second division is the CAMPINE metals recycling, where we transform your lead acid battery out of your car into new recycled lead content, and we refine that and deliver alloys to different applications. And in this area, we also recycle tin, antimony, silver, and gold. Some key figures. We are in business since 1912. For the antimony itself, it is already from the 1935, where we produced antimony trioxides for the X-ray tubes of the old televisions. Later on, we developed two new applications of the antimony trioxides. We are the largest global player of antimony outside of China, with some other with one major competitor in Europe. We are with 195 employees. We are, of course, ISO certificated. We are a Seveso company. But also, I want to stress that we are an active member of the International Antimony Association, and so take care of all the WEEGE aspects. We are lead registrant of several antimony products. Our vision is based on the long tradition of recycling of lead acid batteries, which is the best recycled item in the world, I think, with a lead recycling rate of more than 99%. You don't find any other metal which is recycled that much. So from this tradition, we built up our vision. we want to contribute to a safe, zero-waste society, and not only looking to what is to recycle, but we also want to bring products to the market which are really material solutions. And for this, we contribute to different projects. First of all, the use of antimony and antimony trioxide in the world. Yeah, some history. The first fan of antimony was probably Cleopatra, because yeah, it was used in makeup, just as a small introduction. And the second use in history was a pill. It was a popular remedy for constipation. You just had to take the pill and yeah, your problem was solved after a while. But yeah, current applications are more, yeah, are not that fancy perhaps, but are more to the point. First of all, antimony is used in a lead matrix. The main application is the lead acid battery, but also in radiation protection, it has a use. That is mainly in the form of antimony metal. In the form of antimony trioxide, it is the best synergist for flame retardants. I will come back on that later, but here you see some applications, of course, in cables, but also in PVC tents and foils. It is next to the fire retardancy applications also the best performing polymerization catalyst for PET. In every bottle you buy, there is some minor amount of antimony trioxide, but it was yeah, the main ingredient for the final result. It is also regarded as a very special component in the military industry, for instance, in night vision goggles, because the antimony trioxide is used for clarifying or degassing optical glasses. And next to these applications, we have also pigments which are based on antimony trioxide. In new applications, antimony as a metal can contribute to a thermal electric generator that is generating electricity out of heat. So it is an intermediate to generate the electricity. But also in new applications for energy storage, antimony plays a big role. Here you see the Embry battery. Embry is a new player on the market for a liquid metal battery, which is intended for long time storage of, for instance, solar or wind energy. Okay, I come back on the use of flame retardants in plastics. Yeah, you all remember, I think, the Grenfell Tower incident some years ago. But it's not only that one incident that came in the press, which is relevant for fire retardancy. Over 2.5 million of fires exist each year in Europe. And you see that the time to escape out of your house or room or wherever the incident takes place is getting less year from year because we use a lot of plastics. That's where you had for instance, 17 minutes to escape. In the past, where a lot of wood was used in your house, now it's coming to 3 minutes because there are so many items out of plastics. When you compare that with the time that firefighters need, I think 8 minutes is a minimum that they get to your house. So it is very important to use flame retardant plastics, which give you more escape time. They can give you the 20-minute time frame, which give you the time to escape and give you also the time to the firefighters to come and rescue you. I was very amazed about the frequency of these fires. When you translate it in something that you can feel, that you know that every 3 hours someone dies in a fire. That's a very huge amount. So it is very important to use flame retardants. Even we will increase that risk because we will use electrical vehicles, chargers, 5G, solar panels, and so on. So it's getting more and more important. What are these gas phase flame retardants do? They scavenge the reactive free radicals. They look for inhibiting the flame propagation. They reduce the heat. And you can get several examples of that, of which the halogenated flame retardants are a very important fraction. Antimony trioxide is not that flame retardant, but it is a synergist. A synergist is not effective by itself, but it will improve the effectiveness of that primary flame retardant. And they can add on the reduction of the flame retardant itself, but it can also help for smoke reduction, afterglow, smoldering, and that kind of things. When you look to the use in flame retardants, the main applications are the thermoplastic products in which you get a lot of flame retardants, but also PVC, which has already a flame retardant inherent specific attribution, and also textiles and rubber are applications. You see here the contribution of the different flame retardants itself. Of course, the most important one are the mineral flame retardants, but they have a problem because they have a lot of weight and you have to add a lot of minerals before you get the right flame retardancy. That's the reason why also other flame retardants have their place on the market. The main one is the bromine type, together with the chlorines. And you see here the contribution of the antimony trioxide. In general, it is in the application as 1/3 of the bromine fraction. So 1/3 is replaced by the antimony trioxide synergist. The halogenated substances, I already told you, they are effective in low doses. They have a good thermal stability. And because of that low doses, they have also a minimal impact on the physical properties of the polymer. They have also a good price and performance versus performance ratio. In these halogenated flame retardants, the main used synergist is antimony trioxide. The brominated flame retardants on itself, they have, in fact, they are designed for recycling because they keep their performance also very well after the use. So here you see an example of ICL who investigated the polyamide compounds with flame retardants. It's perhaps somewhat too small. I think I did put some animation, but it doesn't work, I guess. So I hope you can see it, but the upper graphs, they are different brominated flame retardants, some with antimony trioxide, some without. In general, you see that the antimony trioxide contributes to a higher impact strength and has the same tensile strength curve. But what you, and the red one is one of the major commercial non-halogenated flame retardants. What you notice is that they start with a lower impact strength and a lower tensile strength. In general, after recycling, there is a decrease of impact strength and a decrease of tensile strength. But yeah, as the flame retardant plastics with bromine types are starting from a higher impact strength or a higher tensile strength, they keep it also in a better way after recycling. So here you see the reference, which is the first use. After 4 uses, so after 4 times mechanical recycling, they still keep a higher performance than their comparative non-halogenated flame retardants. But yeah, it is not we are not yet there. At the moment, we cannot directly detect the new brominated flame retardants yet out of the older ones, and that is one of the problems. So we have to recycle also the old types, which were perhaps persistent organic compounds, flame retardants, which we have to get rid of because they were environmentally not accepted. The antimony trioxides can contribute to this recycling potential because it has a high weight. It helps, in fact, to sort the flame retardant plastics, brominated flame retardant plastics, out of the cycle. You have seen the density separation. So the antimony trioxide looks for the higher density and give you a way to sort. And of course, yeah, the projects in which CAMPINE contributes do help to recuperate the antimony trioxide out of the older types of plastics. It is it's good to know that the antimony trioxide itself is not lost. You can recuperate it, and it can regain ever and ever his specifications. So antimony coming out of these new recycling trajects can still be brought into the new supply chain. What is this supply chain looking at? Okay, in general, there are 2 types of consumption of antimony metal. The first one I speak about is the red part. It is the metallurgical consumption, like we call it. It is the use in batteries or in other applications where the antimony is used as a metal or in a form of alloy. out of this consumption, you see that it decreases a little. That is because in a lead acid battery, there are new types of alloys used, which contribute to the longer life of the battery or the maintenance-free aspects, and it's the calcium, aluminium, lead. So in future, there will be an over amount of this antimonial lead, which we can use for the recycling of pure antimony trioxide. So let's summary. In this metallurgical consumption, the antimonial lead was always recycled, but as an alloy, and in future, or currently CAMPINE can recycle the antimony content into the pure antimony trioxide, which we can use for the flame retardant applications. For the non-metallurgical consumption, the main consumption is in the flame retardants, but also in glass. I already told you, glass modifier, clarifier, in fact, or in ceramics as a pigment. That are the main ones. In these applications, we are not able to recycle the antimony trioxide yet. Because these plastics, for instance, are not recycled yet. So we have to look to the primary way and of production. And I will tell you a bit about the trajectory it takes. So we start from the mining. We start with ores. In the past, a lot of ores were coming from China, but in the meantime, the depletion in China is yet there. More and more of the ores have large impurities, so they have either to tackle these impurities, either bring ores from the rest of the world to China. Here you see some of these trajects, so the red ones and the blue ones. You see that they all go to China because the main production capacity for producing antimony metal or antimony trioxide is still there. So even when they have other sources in use, they are not yet produced somewhere else. So the dependency of the rest of the world, like CAMPINE, like some other producers in the US, are still using the monopolistic antimony metal of China. You see some new trends on the market. For instance, you see here the SPMP, which is a new roaster in Oman. So perhaps in future we can see some changes so that the ores also can be reproduced at SPMP. But in general, China keeps to have the impact on the pricing and on the availability of the antimony. As some of the other speakers already said, we want to get rid of that non-European monopolists, and we want to have the production somewhere in Europe in which the recycling can help a lot. It is recognized in Europe. Some of us already told, the antimony is regarded as a critical raw material for Europe because of its supply chain. So you see it increasing year by year, that the supply risk is really there. And yeah, what we intend with all the CAMPINE projects is that we can decrease this supply risk in a good way. So by recycling the antimony trioxide in our applications, we will decrease the supply risk. We will increase the recycling rate. I already told you that antimony is recycled, yet it has a recycling rate of 28%, but it's coming only from the metallurgical applications, not yet from the other applications. And of course, we will increase in that way to increase the recycle plastics too. In summary, the vision zero for CAMPINE is that, of course, we want to design for recycling. We want to introduce flame retardant systems which you can recycle. But seeing the diversity of all the applications, seeing the non-detection yet of which bromine types is used, it is very important to tackle intermediately all these problems. So not only the POPs, but also mixed plastics, non-sortable fractions, the diversity of all the plastics and the other plastic ingredients. It is really needed to have better solutions. And for this, we regard to the LIFEPlasPLUS project and the Plas2BeClean project, of which you will hear later on. They will not only recover the antimony trioxide, but also bromine, titanium, calcium, and other ingredients, of course. And in this way, we want to contribute to close the loop of flame retardant plastics. Thank you.
Thank you, Hilde. Thank you for this great presentation. You're the last speaker before the panel, but if I may, I had a quick question for you specifically on your topic. I'm really happy you brought up the subject of lead recycling, because I think it's the best case where we have close to a full loop recycling of a metal. And that also brings in the topic of the batteries. You mentioned something about the EMBRI project, and this possibly being related to the battery field. Would you like to comment a little bit more on this, or is this appropriate at this stage?
Yes, I can. Yeah, Professor Sadoway from MIT developed this liquid metal battery. It was already there as an idea for a long time, and he really investigated it very well, but came to the conclusion that the calcium antimony system is the best way to do it. And in fact, it is a high temperature battery which can hold the energy for a long period of time. So it can be an added value for gaining the solar energy or the wind energy. So you just put the container next to, for instance, your windmill, and it can help not only to collect the energy, but it also can help for bringing the energy at the right moment. So it can store it for a long time. So in this way, it is a very safe battery, and it is now on the market, but still on a small scale in the US. But they will be there in some years for more applications and come also to Europe.
So that would be an alternative to vanadium flow redox, or like a complement, let's say.
That kind of things, yes. Yeah.
Okay.
And I think every battery has its position. Yes. I think we have lack of material for every kind of material. So I think every battery has to contribute in a specific area.
Okay, thanks. Maybe I will ask the floor if there's any specific question for Hilde on her presentation. You can either contribute to the chat or raise your hand. If you need a little bit of time to think, don't worry, because we'll now move to the panel. So you'll also have the occasion to interact with all speakers. So if that's it, I would like to thank you very much, Hilde, for your contribution and this presentation, and invite you to stick around. We'll have a 15-minute panel where we can further discuss and give everybody the opportunity to provide their thoughts and exchange on this. I think our technical expert Jérôme is going to try to align us in as much as possible into a real panel. So we have to give him, I think, a minute or so, because don't forget, this is the best we could do without being live. There we are. I think we have a panel view here, and this is a kind of a little gimmick. Oh, I can see Patrick is going, wow, this is amazing, isn't it? Right? Well, you don't stop technology, right? So there we go. So, well, thank you very much for being part of this panel. And maybe I can sort of get going with a general question. And I think I will refer to one of Hilde's latest slide, or I think it was the slide before last, where you rightly pointed out the role of antimony as a critical raw material. And you stopped at 2017, but there's been a fourth list, which came up in 2020, and antimony is still there. It's still a critical raw material. This list is kind of highly skewed towards metals, really, metals and minerals. And also, obviously, there are some of our typical battery metals. Cobalt's been there for a while, and lithium has appeared in 2020. So we can clearly see that this is playing a role. So my question is to this panel, and whoever wants to take the lead is most welcome. Can we envision at some point thermoplastic being on this critical raw material list? Because it doesn't say critical raw metals, but it says critical raw material. So I guess it would qualify. So if anybody has a good thought to sort of kickstart the discussion, be my guest.
If there's no one else, the critical raw materials list was, I believe, and correct me if I'm wrong here, envisioned by more of the metal industry. So probably that's also one of the reasons why you don't have many organics in here, or actually any. It also fits very well with a nice periodic table of elements, so you can understand it better. Whether or not plastics would deserve a place there, maybe. Right now there are shortages. However, at the same time, we also have to recall the situation at the start of the COVID crisis, when everyone was ramping down production, when polymers were dirt cheap. It's maybe in the future, but for the time being, I don't think the situation is so dire that we should classify plastics as a critical raw material. But perhaps others have other ideas on this.
Yeah, I can also, from my point of view, I do not see plastic material as comparable to the metals elements like antimony. I can say that we are facing shortages in this month, and also due to the mainly due to the to not only to logistic but also to capacity, production capacity, like for example for polyamide 6,6. And then it depends from the investment that will be done in the future on the production of this kind of material. That I think is more related to which will be the investment on each plastic families, and in which region this investment will be done. Okay, because this is also something that we are facing right now. If after pandemic, China market started very aggressively, very fast, and the export that usually they were doing was decreased because they had to supply the internal production. Then this will be a key, I think, for the future to understand what we would like to do as Europe.
Well, thank you for these views. I don't know if there's any other ideas on the subject. Otherwise, we had a question from the audience. A person named Chandra wanted to ask a question. I think this would be a good time if Chandra hears me. He can directly interact with the panel and ask the question.
Hi, good morning to all. When we use my question is related to the recycling material. So my question is, what is the percentage of recycled material can be used to produce the part? And if we use the recycled material, so it is a bit chances like the processing is a very bit difficult, and there is a chances of more defects on the final part. Then is there any mitigate for this? So
I can try to start to answer. Okay, first of all, from our point of view, we are not indicating a limit. Okay, then we can also think to use a 100% recycled material. But obviously, we are not indicating a limit from the point of view of the recycled percentage, but we are indicating limit from the point of view of the properties of the material. And then this means also the characteristic that the materials has to fulfill to be able to process it like a virgin one. Okay, then not all the recycled material will be used for our application, but only the ones that will be able to be processed like the virgin one. Okay, then surely this is a challenge for the compounder, but from the point of view of the process, if from the point of view of the mechanical properties, we have done a certain adjustment from the point of view of the processability, we are asking more or less the same. Okay, then the shrinkage, etc., etc.
I can add a little bit to this. And it is a difficult question because it depends very much on what you're trying to make. It's not by coincidence that the construction sector is taking up such a large amount of plastic recyclates, because there are certain articles in there that are not so demanding. Yeah, the best example is these foots for road furniture. I mean, you can basically chuck any plastic in to that compression mold system. As long as it sticks together, it's fine. Getting 100% recycled content there, relatively easy. But then, you know, you can't make an entire world consisting out of park benches. You have to do something else, and then you try to move into sectors with high quality demands, such as the automotive industry. Yes, there it becomes a little bit more problematic to reach physical mechanical properties. But then again, yes, okay, maybe some physical mechanical properties are over-engineered, but you also have to acknowledge that, yeah, there are parts in cars that just don't really need to be extremely sturdy. And if recyclate can't meet it, yeah, then you will have a lower percentage of recycled content, or even none. And it is also a little bit of a balancing act for recyclers. Because if you want to get a higher product quality recyclate, you are going to be generating more residuals, because then you are creating a greater purity products, creating order out of chaos, which would meet higher specifications, but then you will have a residual fraction which is greater. So then there's a last part to this question: how can you mitigate all of this? Well, first of all, there is something that can be done upstream, designed for recycling. Now, this is less relevant for longer life cycle products, but for short life cycle products such as packaging, you produce the packaging in a few months, it reaches a recycler, maybe even weeks. It's a very short cycle in terms of time. There have been massive advances, and we host the RecyPlus platform, where we have brand owners and recyclers talking to one another about how can we make packaging that's beneficial for recycling and generates less residuals. Downstream, at the recyclers or even at compounders, they also have a role to play. You can also have mitigating technologies, new stabilizer packages, new antioxidants. The magic of additives can be used to increase, to upgrade plastics as well. And quite a lot of recyclers have actually also moved into that process step of compounding and started developing specific competency in rejuvenating the recycled plastics that has gone through use phase. So that's a little bit our view on this. Chandra, I don't know if this answers your question or not.
Yeah, no problem. I got this. Thank you.
Maybe just a word to explain our philosophy by Comet EEE.
Hervé, you are.
Hervé, we don't hear you.
So now it's okay? So since 2012, since we started the recycling line, plastic recycling line by Comet, we saw that if we want to put the recycled material easily on the market, you need to produce high quality plastics. It means that the percentage of recycled content in a part is depending mainly on the quality of you can reach. So if you have a very high quality, you have more opportunity to recycle in high level application. So it's important to have this quality to help the end user to integrate your recycled material. If it's low quality, you cannot do, you can only produce low added value parts. So it's the key of the recycling. Do the best material to help the circularity, because if you produce shitty material, it's impossible to do something interesting with it. That's the topic. That's our goal, is to maximum quality, to guarantee, to ensure, to be able to reintegrate the circularity. If not, nobody wants your material because they cannot use it. Or if they use it, it's very, very low content, because if the quality is too low, they can use maybe 5 or 10% in the recipe of the compound. That's all.
Yeah, agree.
Yeah, I can confirm for the antimony trioxide, we will of course try to integrate the antimony trioxide as soon as possible. So for the beginning, you can start with applications in rubber or whatever, where the color does not matter that much. But our final goal is to produce an antimony trioxide that doesn't differ in anything from the primary material. Which we already can. Not from flame retardants, but from the metallurgical incoming fractions.
I have a question. It's Benoit from the CTP. You can hear me?
Yes.
It's okay. Just I have not a clear view of the trends in the manufacturing of cars, but my question is, do you think we will use more and more reinforced plastics, composite, carbon fiber composite, like materials like this in the manufacturing of cars? And if yes, will it remain limited or not? And what will be the impact on the separation techniques and the quality of the product, and in fact the recycling? Because I don't think there is not so much solutions for the composite, and maybe it will interfere during the processing of recycling. Maybe it's not a problem if it remains limited in the car, but I don't know. So if you have some insight.
You are meaning the application of thermoset material, or
I'm talking about composite, so glass fibers, carbon.
Okay, but thermoplastic with carbon and glass fiber, or thermoset with plastic and with carbon? What?
Thermoplastics.
Thermoplastic. Okay. Okay. It depends. There are some studies. Speaking about, okay, a little something about thermoset. The thermoset are used mainly for sportive car, but low numbers. Okay.
Yeah.
Instead, thermoplastic. For example, there are some studies to evaluate the application for battery, because as we said before, battery are EV. We have to think how to decrease the weight of the battery. Currently, they are made mainly of steel or aluminum. If we are speaking about the battery box, okay. And there are some ideas to think on thermoplastic reinforced materials, for example. But I can say for sure that this will be the future solution. Okay, we are thinking on that.
So you think that it could be used more and more in the future, even if it's limited now?
At the moment, there are some applications, but not so much. Okay.
Mm-hmm. Okay, so it's not yet an issue at this stage.
No, at the moment, no. In the future, I'm not so sure, but anyway, it will be big components, then easy to be separated by the car. Okay.
Mm.
Yeah.
Like a bumper, it's easy to separate a bumper from a car. In this case, they will be probably big components, easy to be separated. But I can say that at the moment that for sure this will be the future solution. Is possible.
Mm. Okay.
Yeah, maybe to add to this, the reason you're asking the question is because you might have heard that recyclers don't like glass fiber reinforced polypropylene.
Mm-hmm.
Yeah, we don't. I don't know if you have the magical solution, because you seem to be quite advanced on dealing with glass fiber reinforced PP. But normally it's not great for recycling. So from that perspective, you would want less of it in automotive vehicles. On the other hand, we do understand that there is a desire to have cars that are as light as possible.
Yeah.
And if you can replace steel with something that is lighter, and then that car goes onto the road for 20 years, yeah, you can imagine the CO2 savings on that one. So it is a bit of a difficult discussion, and you have to be cautious of getting too categorical about whether or not this is a good thing or not.
Mm.
But Hervé, maybe you have some additional insights to share.
Yes, the problem with the composite, of course, everybody has to know that the thermoset is not recyclable, because they are this material, every kind of composite, they have to be maybe cracking to try to recover some fibers. But the economical point of view, this recycling is very, very complicated. And if we talk about composite fibers into thermoplastics, for example, PP glass fibers or like that, it could be recyclable, but not yet at the moment by Comet. But this should be, we should work on it, try to arrive at this situation. But of course, composite is more complicated than the pure material. Those kind of, but we are talking about FPP. FPP is one kind of composite, because we typically is a PP with a 20% of talcum. Mm-hmm. But it's easy. It's classically very more easy than is easier than a recycling glass fiber or carbon fiber. So it's two words. So for the future, we have to work on it. But I don't know if the car manufacturer, the end user, will accept to reuse this secondary PP glass fiber, for example. That's for the topics. And we will analyze it, and we are working on it, because I told you that we are also working on another R&D project where we are facing to this problem is to recover the technical plastics and heat plastic with density over than 1.08. And then in this density range, you find, for example, the PP with 30% of glass fibers. So maybe in 1 or 2 years, I will come back to see Gabriele and say, no, I have this recycled PP. What can we do together with this one? That's one of the targets of the R&D project by Comet, to find a solution for this. So we did it for the FPP with until the density 108, to know what will be for the next steps. And for example, there is also another, if we spoke about the electrical appliances, there is also the PP with 40% of mineral filler. Typically for the washing drum, there is also another topic to work on it, because there's valuable plastics, but how to reach to separate them, and because at the moment it seems it's complicated to have a right and profitable and industrial process to be able to put in production. That's mainly the problem. But we are working on it. But of course, I think the most complicated will be the thermoset with glass fiber or the carbon fibers, because you have to disintegrate the thermoset. And I don't know if the value of the glass fiber or the carbon fiber will pay the process, because as everybody knows, the glass fiber is not expensive. Okay, carbon fibers has a price, but it could be, I don't know if it's profitable. That we will see in the future in the reality, but I'm not convinced that we can pay the thermoset recycling. We will see in the future.
Is there discussions between the recyclers like you and the designers of cars? Because you know, if you build,
I think there is, because we are talking. For example, this kind of project is a good illustration that there is a discussion, of course, but because we are talking about the PP that and so on. But of course, we are not yet involved to say, we want to put a thermoset. What do you think about that? Or so. Of course, if we want to have an easy car for recycling, it will be with pure material and without mixing, without glue, without multi-layer material will help. That's okay. The designing, I think, to help the recycling is to think that after that we have to separate the material and to do it industrially, because I think that dismantling, everybody is talking, oh, you can dismantle. You have to know that dismantling manually is very costly. It is very high cost, and sometimes it's impossible to put this at industrial level because it's too expensive and the value chain is impossible. So of course, some competitors they extract the bumpers by hand. Okay, but that's maybe the only one part that we can see in the global recycling of the ELVs is that only the bumper is extracted because they don't have a plastic line after. But after, if we ask to extract one small part in the motors, nobody will do that because it's too complicated to have the time to go into the motor to extract, to take away the screw and then to separate. You can forget. Economically, it's impossible at the moment. That's why everything is shredded to separate as fast as possible to recover directly the material with higher value to pay the process.
And this is not just a view of Comet, this is the view of the plastic recycling value chain. Dismantling, seriously, it's not going to happen. Maybe bumpers, maximum maybe fuel tanks. But if it's not large enough, it makes no economic sense.
What we do
unless there would be a substantial increase in the amount that automotive treatment centers receive from EPR schemes that are around cars. But I don't see that the producers of cars would love that. Now would they?
At the depollution center, what is interesting to dismantle is the spare parts for second-hand pieces, second-hand parts. It has also an important role in the global value chain of the recycling ELVs, but it's never for the material recycling. It's always for parts, mainly. That's why everybody is working on post-shredder technology to separate the material by qualities. But we have to work on this complicated stream, of course, like PP with 30% glass fiber is one of our topics. But for the thermosetting, what will be possible by Comet will be to crack this material and to recover energy of this. It will be with those kind of material will go with the fluff, the unrecyclable material, to produce heat and electricity. And of course, black carbon, because it's the residues of the thermolysis cracking.
And you think you would be able to separate it from the other polymers, or it should be difficult?
It should be difficult. It depends on the density, the material, and how to separate a material if there is no value.
Mm-hmm. Yeah.
We don't want to, until now, we separate always to get to separate valuable material. If we have to separate a thermoset without any value, who will pay the process? If there is no economical interest, it's complicated.
Okay, thank you.
Thank you very much for this this panel and this great exchange. It was a pleasure to have you all participate in this morning session, and I hope it was as constructive for you as it was for the audience and myself. We had promised a visit of Comet's industrial site. It's not possible directly, but we'll do our best to try to compensate by showing you a video, and I will let Hervé introduce this video. Hervé, the floor is yours. You can move on with this introduction. Thank you.
Okay. Thank you, Philippe. First, of course, the goal was to invite you to visit the global value chain of the recycling of end-of-life vehicles and WEEE, but with the COVID situation, it was impossible. So this video will present you a part of our activity of the ELVs. It is focused mainly on the plastics, because as you can see, you can read on your screen Plastyriner. So I would like first to thank you, Plastyrine, for this video. Of course, Plastyrine gave us the opportunity to participate to concours, to a challenge, to present new development in recycling and in plastics in general, because Plastyrine is the Walloon plastics cluster. We are candidate, and we are the three finalists, three laureates. I don't know if it's in English, but the three finalists of the Plastyriner, and to present our innovation. Plastyriners give us a budget to produce this video to present the innovation. So this video, we thank Plastyrine, and this video will present you the development we did on the FPP for this project LIFE PlasPLUS, and it will be the start of a coming soon video that we will produce to illustrate the global project, the global LIFE PlasPLUS project. In this video, we don't focus on the depollution and on the dismantling of the ELVs and the WEEE, because we focus directly on the plastic line. So we can start directly with this video showing you the plastic line by Comet.
Dans le groupe Comet, nous recyclons tous les déchets métalliques. Ce sont des véhicules hors d'usage, les déchets d'équipements électriques et électroniques et la ferraille au sens général du terme. Notre devise est toujours de recycler à l'infini. Pour y arriver, nous avons commencé à recycler les plastiques dans les années 2012. Nous voulons aller toujours de l'avant et donc recycler toujours plus, c'est-à-dire d'aller rechercher des plastiques de plus haute pureté. Donc nous avons dû développer un procédé pour purifier et séparer la fraction PP chargée que nous appelons chez Comet le PP chargé. Dans le groupe Comet, nous traitons 1 200 000 tonnes de déchets métalliques. Comet Traitements va traiter 350 000 tonnes de déchets résidus de broyage. De tout ce grand volume, nous extrayons de l'ordre de 15 000 tonnes de plastique retournant vers le secteur du compoundage. Ce démonstrateur et l'industrialisation de ces technologies va nous permettre de traiter, de produire 2000 tonnes de FPP et de 4 à 5 000 tonnes d'EPS et d'ABS. La spécificité vient du fait que nous faisons face à un mélange ternaire de plastique, donc de mélange de PS, d'ABS et de PP chargé. Les technologies habituelles présentes sur le marché ne permettent pas cette triple séparation. Par notre développement, nous arrivons à purifier ces trois fractions. Nous vous présentons ici le PP chargé qui atteint des puretés de plus de 98%, avec comme objectif visé de réintégrer le secteur automobile pour boucler la boucle de la circularité. Nous sommes dans un projet qui ne fait pas de downcycling, mais du upcycling. C'est-à-dire que nous partons d'un déchet, typiquement ici un véhicule hors d'usage, et nous reproduisons une matière première qui va être utilisée pour refaire des pièces automobiles. C'est une vraie circularité dans la mesure où on part d'un déchet automobile, on retourne dans la pièce automobile et la boucle est totalement fermée.
Voilà pour cette vidéo. Évidemment, on aurait vraiment aimé vous montrer tout ça en plus de détails, mais vu la période plus vite, nous en avons été empêchés.
Thank you, Hervé. I think that concludes our morning session and our presentation. So we'll take a pause to have lunch now and encourage you to participate this afternoon. So thank you very much and see you at 2 o'clock.
Shortly introduce you what we are doing at TNO, because I think there are some other topics where we're working on that is also relevant for you project. And then I'm going to the next slide. So this is in short giving what TNO is doing. So what we would really like to do is to close this, the value chain. So starting from production, going to the end user, going to the consumer, then it is collected, coming waste, and then it is recycled again. And TNO is working on several topics. The one is the system integration. So how can we make the system work? How can we connect the value chains so that a producer is talking with somebody who has to sort it or has to recycle it? Because these are different worlds and they have to connect to each other. And that we do also from a cost perspective. How can we make the business case, but also from a life cycle assessment? What are really the sustainable options? Then we work also on technology. So the design for circularity, we focus on packaging, on the sorting and washing, so including pre-treatment. We develop recycling methodology, so that is the thermochemical recycling. I will tell you in a minute more about it. Depolymerization and dissolution. And dissolution, that is the Plastic to be Cleaned project where I'm going to talk about. And also one of the topics which get more and more interest is also the microplastics, where we have to deal with and how can we prevent that the microplastics are formed. So not only looking at what the risks are, but also the prevention, and that can be done, for instance, in the design. So then I would like to focus to show you two technologies that can, I think, be of interest for you, and one that is a pre-treatment method, and that we use to deal with packaging waste, for instance. So the DKR 310, which are the foils and films, and there we have a heterogeneous plastic waste. We melt it, we crack it due to and it cracks due to cooling, and then we get really fine granulates. And we get really some nice results for that, because we are able to really to diminish the chlorine compound of it. So even if PVC is present, the chlorine compound is going to be lowered. And here you see some of the results. So what you see is that the ash component is going down, which is good, and also the strong reduction here you can see from chlorine and from sulfur. And I think this is one of the promising methodologies, but we have to go further, and that can help us also for processing other types of waste, to do the pre-treatment before the mechanical or the thermochemical recycling. And here there is another technology. What I would like to share with you is the thermochemical development. Well, pyrolysis, gasification, I think you all know about it. So that is what we're doing in the field of recycling. And what we then see is for the what we have developed is a gasification, or maybe it's better to say in high temperature pyrolysis of thermocracking procedure, in which we go in one process, the Milena-Olga process, to the green heat power, green gas, and the green chemicals. And this is used for more types of I have to click through, for more types of waste that we can put it in. But I would like here to focus on the plastic waste. And there you see that we get really a nice output of methane is in it, of well, higher of C2 of the olefins, a small part of syngas, and also some CO2 of course. So, but this is really a nice output for dealing with plastic waste, and of course we can also fine-tune this more in the next future. Then coming to plants to be cleaned, because that is the real topic of the project. Then, as I already said in the title, what we would like to is to close the loop of the polymer of the brominated flame retardants and the antimony trioxide for WEEE plastics. So what we focus then is on HIPS and on ABS. So those two polymers who are largely used in WEEE plastics. So what is important is that we separate the polymer from the fraction, and also recover the different additives, and we will do that in an economic viable manner, and also it should be more environmentally friendly than the current methodologies that are currently under development. Here you can see the consortium, and this is typically how we work as TNO. What we would like to do is to connect the whole value chain. So as you can see here, we have the whole value chain in this project. We have the recycling company, who's Coolwack. We have an engineering company which helps us with the designing the equipment which is needed. We have for the polymer, for the ABS, is Alix is on board, and also an end user, Electrolux, so we can test the recycled product also in a real life application. We have ICL for the bromine recovery, and we have CAMPINE for the antimony recovery. So, and here these are the three research institutes, and that's sustainable innovations for the dissemination. And here you can see what we aim within the PLUS to be cleaned. So we start with the first step with a mechanical pre-sorting technology. And in this step, we are going to separate or to sort different plastics already from each other, to have a stream focus on HIPs and ABS, and preferably only with the brominated flame retardants, because the other ones, they can be recycled with other methodologies. And then for the stream that contains the brominated flame retardants, we would like to close the 3 loops. So that is of the polymer, so that is the ABS or the HIPs, the bromine and the antimony trioxide. And then we would like to do so that is actually what we're doing, what we are now at the lab. And then the next step is the process integration. And also we are going to scale up that. So we are going to kilogram scale then. We do the performance testing of the process and the product. So we are going to apply the product, the recycled polymer in a real life application. So that is why Electrolux is part of our consortium. And here it's not step 5, but we're continuously doing this, is the system optimization for sustainability and also for economic viability. So just to summarize the main results, and I'm going in a minute more detailed into these results. But for the first part, the pre-processing and the sorting, so the Raman equipment is set up in the spectral library so that we can separate the mainstreams of the WEEE plastics. So we have the dissolutions under superheated conditions we have set up. We did over 300 experiments, so did really a lot of experiments. And well, actually, it is not an easy process that we developed, but we are quite far for the removal of the antimony trioxides, which is already on specs, and the removal of bromine. Well, it's almost on spec. Sometimes it's on spec and sometimes it's just above. And that we are now testing also with real life samples. And also the impact assessment, what we did at the start of the project, that we did a quick scan. And then we saw a real benefit of using the PLUS to be cleaned process compared for incineration, what is done nowadays. So here I'm going more into the details of the project. So this is the first work package, which is about pre-processing, the sensing and the sorting, which we do with Raman spectroscopy. And this is to identify all the colored polymers, including black one. This is also our target. I have to admit that the black ones, that are really the ones that giving problems. And well, actually, it's a known problem in the recycling, that black ones are the most difficult ones. But we had already good results with the colored polymers. And then in the next work package, so in the next step, there we are going to do the dissolution. So that is then, we work then on HIPs and ABS. And for one of those polymers, and currently it's under discussion which one we are going to scale up, we are going to scale up. And they're under superheated conditions, so that is under a bit of pressure just above the boiling point, and then you get better separations of additives. We recycle the polymer and also the brominated flame retardants in the antimony trioxide. So now we are on lab scale, and the next step is that we come up to TRL5. And then here you can see how we did the experiments. So we started at really low scale, just in glass tubes, doing solubility experiments. Then we went to somewhat lower scale, and you see here that these are glass bottles, so we can see what happens. That makes it easy to develop the process. So here you see already the scale up. So this is at 2 liter. Fat, so at 100 grams is we can deal with in this process, and we would like to make a continuous process on it, and the scale up is done at Fraunhofer. And here you see in This is not a complete unit at Fraunhofer, but just some part which we use for this project for the solutions. So here you can see what the process is look like. So we start with the samples, we do the dissolution. So this is in TNO. We can still see what happens. Then we have density separation. So additives are then collected. Then another step, that is the hot filtration, and finally we have the spray drying, and then the polymer is recovered. So this is we do for the B plastics, but actually at TNO we are looking also at other streams as well, like olefins of polycarbonate, for instance. So that is where we work on. So then the performance testing of the polymer. So what we do is actually the polymers, they should comply, of course, with REACH, otherwise they cannot be used in recycled as recycled material. So we check for the removal efficiency assessment. What is the quality of the polymer? What are the requests for the end users application, and also what is then the output of the bromine and the antimony containing fractions. So we check whether the bromine it meets the bromine limits. Then finally the environmental assessment. So the goal is that we have an environmental sound and economic viable process, as what is said in the beginning. So we looked at the sustainability from a life cycle assessment point, and we did it in two ways. One is going from the looking from the materials side. So that is this 1 ton of B plastics. We have then in a defined average composition particle size, and we are looking how this what this the life cycle assessment result is, and also from a product perspective. So then we are going to look into real product, and they are given here on the next slide. This is the washing machine, in which we use in the internal door frame ABS, and then we have assumed 220 washing cycles per year, and then equipped it in a lifespan of 10 years. So you have 7,000 running hours, and the other one is that we have the inner liner of a household refrigerators cabinet. And that has also a running hours of here, over 78,000 hours, and a lifetime of 9 years. And what we see is that for the glass to be cleaned in the quick scan, that we see that for HIPS and for ABS, you see that the emission of CO2 is less compared to the what is now done with this type of waste, that is incineration with energy recovery. So both HIPS and ABS score better, and here you have the overall score from the process. Also, the live costing showed that there was a significant reduction of the cost for using recycled ABS and recycled HIPS. What we have to say now is this was done after 1 year of the project. So now we are continuously working and fine-tuning the project. So we have to update these figures also with the new data. And also we did this only for the polymer. So as we also going to recover the bromine and the antimony trioxide, that will also give a benefit which is not included in these data. So then I would like also to if you are interested in it, that you have a look at our website. So we have a short film about a short video about gloves to be cleaned, and then you can see all the ins and outs and why we are doing it. And of course, but I think most of you, I do not have to tell that yeah, the WEEE additives, they do contain often legacy additives, so that the additives that are were allowed to use in the past but not allowed to use anymore, and that is the reason why we really have to make these new recycling methodologies, and why we not can yeah, easily go to mechanical recycling or other options. So we should make sure that those legacy additives, that they are removed and that they are below the limits that are given by the EU. So then the summary of the project. So Plus to be cleaned is about closing 3 loops. So we start with the pre-sorting, so sorting different types of plastics, and already did do some purification step for that, so that you have as clean as possible, so as most focused possible stream of plastics, which we do under the which we then deal with dissolution and the superheated conditions, so to recover or recycle the polymer, the bromine, and the antimony trioxide. The scale up that we're doing at Fraunhofer, so to go into kilogram scale, and actually because we have we have under pressure, and we would like to go to a full continuous process, the performance testing. So that is actually we have to do at the end of the project, when we made this material, that we do it also, that we test it in a real life application, and the system and optimization. So that is in short what is Plus to be cleaned about. Doing it for WEEE plastics, but I'm sure that we also can develop this types of process or the methodology also for other types of plastics. So here I would like to show you the team that was pre-corona time, that we still could be together in winter. That was the last time that we could meet, and I would like to thank you for your attention, and I think the floor is open for questions now.
Thank you very much for this presentation. This was very interesting. I'm just watching if there are any specific questions. The floor is now open for questions for Esther, if you want. If not, my colleague Hervé had a question that he would like to address, so I'll pass it over to Hervé.
Yes. The question is, I saw that you're interesting result on the ABS, and what happens if we would like to recycle ABS with PC inside or ABS with glass fiber? Is it possible to recycle those kind of plastics or compound of ABS?
Well, actually, we haven't done that experiment at this moment, because we really focus on the ABS, which contains also some parts of polybutadiene in it. But I think the glass fiber that can, yeah, we can collect that in the insoluble fraction. So I think that will work. The PC and the ABS, I know we did some other project on it, and there we were, but that was more focused on the polycarbonate, and there we could recover the polycarbonate. So yeah, I'm pretty sure that we also we have not typically focused in this project that this process can deal with it.
Thank you.
Yeah, thank you very much for this presentation. I'm checking the chat to see if there's any specific questions? Not at the moment, but I think you will stay for the panel, and we can possibly further discuss these issues. So
yeah, sorry, I have to apologize because I have to be also at another meeting at 3 o'clock. So
okay.
That is for me not possible. So if there are questions now, I'm happy to answer. And otherwise, if there are questions for me, then please send them on mail to me and I can answer them at a later stage.
Okay, certainly, we'll do that. We'll do that. We'll make sure we collect everything and forward this to you. Okay. I'm waiting to see if anybody would like to comment.
So actually, I can say, well, if there are any questions, so you can always contact us via our website. So that is www.plasticlean.eu. And also Hilde Govaerts, who is also present here, she is also part of this consortium. So she's also well aware what is going on. And I think if we can connect with other projects or can share knowledge, which is both of benefit, that would be nice. And we are always open to discuss possibilities.
Yeah, definitely. I think there's possibly some synergies as we are also working with antimony, and this is a substance of quite a bit of interest to us, and we're also trying to advance some strategies with CAMPINE. So we're more than happy to discuss and see how we can brainstorm together to push the circular economy one step further. So yeah, thank you very much.
Yeah, and I agree with that because working together, we should do it faster and faster. Each day I'm reading in the newspaper that we should go faster to reach our targets of 50% circularity, or reduction of 50% of the of our raw materials in 2030. So that means that we really have to bundle our knowledge.
Yeah, and especially I think antimony is very specific as a metal. You know, I mean, there's you know, you can talk about copper, platinum, cobalt, whatever, but antimony is very specific in its origin. It's quite dispersed. You can find it in many places, but as Hilde showed in our morning slide, that China is such a predominant source of the material that everything that we can do to try to cut off or actually reduce our dependency is positive. And the conundrum is that there's so much antimony around us, you know, it's everywhere, that we should be able to do that. So definitely we'll try to be in touch.
Yeah, perfect.
Thank you very much. And I wish you a great afternoon. We'll relay the questions, and we'll now move on to next speaker. Thank you very much, Esther.
You're welcome.
Thank you.
Okay, after this great presentation, we are now going to move to the next speaker, who is Petra Ingelbrecht of Ineos Styrolution. And Petra will be presenting the Absolutely Circular project. So if you are ready, be my guest.
Good afternoon. Yeah, good afternoon. I'm Petra Ingelbrecht, Ineos Styrolution. I'm the sustainability manager. I hope you can see my screen in the meantime.
Not yet, but we can see you. We have the connection with you, but not yet your screen.
Yeah, I try again. Share screen. There we go.
Yeah, it's coming, I believe. Yes, it's here. Beautiful. Okay. Thank you.
So first of all, thanks for the invitation. As a kind of colleague within the LIFE program, I'm happy to present our project, which is called LIFE Absolutely Circular. In our program, we start all the way from single-use plastics, in our case polystyrene, and we bring it back to styrene, and so all the way to ABS. Yeah? So we start from single-use plastics to the more sustainable and durable ABS applications. We have 3 partners in our program. We as Ineos Styrolution, I think we are a global company. Over 10 countries with 20 production sites. We have a focus on packaging, but also on automotive, electronics, household and construction and healthcare, which actually allows us everything which we develop on circularity and packaging to also transfer our knowledge to automotive, electronics, household and construction. And what we develop in one region, we can also transfer that to Asia, Americas and vice versa. And that's for us a key asset in the whole sustainability agenda. Another partner of us is Indaver. Indaver is actually a European player with a strong representation in Belgium, who are actually a main waste recycler or waste treatments. So they provide the waste sourcing, they do incineration and in the past also landfill, but they have a whole agenda on recycling. Yeah, and they will be the ones who do for us the advanced recycling. There is a third player in the team which likes to have a bit more confidentiality, but we is actually also a third partner in the group. Yeah. I will skip that slide. So our main aim as Styrolution within sustainability is to work on the circularity of plastics. So what we can do to eliminate plastic waste. And there we have actually a pledge to recycle 30% recycled content for polystyrene, allow our polymers to be recycled, really scale up our own circularity agenda as an Ineos group, and also achieve net zero emissions, greenhouse gas emissions by 2050. So sustainability is a big part of our agenda and a whole strategy behind it. One of the key assets in our circularity agenda is starting with packaging, actually. And it's taking the single out of single use. So here you see a yogurt pot, and here we develop approaches to really bring the yogurt pot back to the yogurt pot. So now downcycling to lower applications, no, bring it back to exact the same quality so that our customers don't need to lower their expectations, their specifications for our products. So how do we want to achieve circular economy? So we take our recycled attributed feedstock from our suppliers, or we take bio-attributed feedstock so that we can replace fossil feedstock. We make the monomer. If we take the monomers, we make the polymers, polystyrene, ABS, and others from it. Then we have the whole value chain, which brings it back to waste. And that from that polystyrene waste, we go to mechanical recycling and depolymerization, which we will explain later on in this project, in this plan. Yeah. For ABS, we also go to shattering, WEEE waste, ELV waste, where we then further mechanical recycle ABS. Yeah. And so here we bring already mechanical recycled ABS on the market with 50 to 70% recycled contents and not and really very similar specifications. So we work on mechanical recycling of ABS, mechanical recycling of polystyrene, depolymerization, so a kind of advanced recycling of polystyrene. And in addition, we replace our feedstock with low carbon feedstock. And we also work together with polyolefins on recycled feedstock from their operations. And that's how we want to achieve 20 to 30% recycled content for styrenics. Yeah. So the LIFE Absolutely Circular program really fits into that, starting with polystyrene, mechanical recycling, advanced recycling, and how can we complement on the mechanical recycling of ABS and also go to that very high qualities due to advanced recycling. Well, that's actually very simple. Yeah. So we start with polystyrene waste, and we have already a collection and sorting of polystyrene available, where we really go for a high quality sorting. Polystyrene is against the perception of the market of NGOs here is really easy to sort out, and with existing near infrared you can only go to 99% quality. And then we bring it into what we call advanced recycling. Yeah, and at advanced recycling, you bring back the polystyrene back to the monomer, so back to the styrene. And that styrene has almost a 50% lower carbon footprints and is also circular compared with fossil waste. So here we take the styrene, we purified it, we take the styrene directly from the polystyrene waste, and we save multiple steps of fossil fuel production with relatively high energy use. So this is circular, and this is low carbon, and this is good for our environmental footprints. So that recycled styrene is very valuable for us, yeah, and that we will then also use. We also use it to combine it with acrylonitrile and with rubber to make our ABS. And so here in the ABS, we will replace the fossil styrene by the low carbon recycled styrene and bring that then back to consumer goods. And you see all the applications we can have over there. So that's basically our principle. And we wanted to demonstrate that at a pilot scale. And this project has really the intention to explain the advantages of advanced recycling to everyone, to our customers, to the authorities, to NGOs, and to really prove that it's technically feasible and scalable, that it has a good environmental footprint, and it's actually better for circularity and a better carbon footprint. And it's also safe, yeah. And we will make small-scale demo examples with our customers so that they can show that to their customers and end users that it's safe, and then we can later on upscale it and transfer it globally. Yeah, so we started already with some lab scale activities on ABS to really show it works. And Indaver is already looking at preparing for an polystyrene depolymerization plant, which will be built 2022-2023 and will become operational 2024. Yeah, so that's the timeline. So we have already showed that at lab scale it really works. It has very similar, actually exactly the same properties as fossil ABS. So we can here, in contradiction with mechanical recycling, afford all the colors our customers want, all the high quality. Even if we go for very high quality for mechanical recycling, you can never have all the features and all the colors which you have with advanced recycling. Yeah. Then the construction of the polystyrene plant is a little bit later, but it's also significantly bigger and announced already. Yeah. And then we work on pilots where we really take the styrene coming out of the depolymerization plant. We purify it to very high purity, similar purities as a fossil styrene. And then we go at the pilot scale and we will make real ABS pellets where the styrene is replaced by the recycled styrene. So no mass balance approaches at this stage, but real tangible ABRS. Yeah, so it will be pilot quantities, etc. Then that go to our customers, and our customer, they will make demo material of it. Yeah, it can be demo toys, it can be also be demo automotive parts or demo households, etc. Yeah, really show it works. If it's all tested, it's safe, it's well understood, then we can of course scale up with mass balance approaches and really bring big volumes into our world scale plans and extend the approach into the 3 regions, which is then our 2024 outreach and scale up approach. Yeah. So here you say, okay, lab scale demonstration of ABRS. This is done. We made some publications about it. We also look in what kinds of polystyrene waste we have. I think the most straightforward solution is, of course, to use your household polystyrene. In Germany, it's called the yellow bag. In Belgium, it's also all collected and sorted. It's the blue bin bag. And there is also waste coming from electronics. So we have a clear view on the polystyrene waste collection and sorting, and we will only look for more waste. There's also some efforts done to look if we can also do some something with littered waste, because we believe chemical recycling might be worth checking it if you can also provide solutions for the problem of marine litter. Yeah, but that's actually not done on the program, and actually as well of interest of our EU officers. The big step, of course, and a big investment is the whole depolymerization, yeah, from polystyrene waste to polystyrene. Here, Indaver is the biggest player with a big plant coming in Antwerp soon, and also looking for upscaling. It is a little bit later as anticipated, but again, the plant is bigger, more efforts needed to do on the collection and sorting plant. So additional pre-sorting has been previewed, and currently the whole of Belgium is already collecting it. New sorting installations are in place. So Belgium is already one of the first movers who will have the full circularity on polystyrene. I think in Germany there's also a lot already ongoing. So in contradiction to pacts aiming for banning polystyrene, for us it's actually a very, very good sustainable source. And polystyrene might be one of the most misunderstood polymers in terms of recycling. Yeah, so happy to show that, and happy to have partners in Europe, Indaver in Belgium. We also have a pilot coming soon in UK, in Swindon, to show also in UK this works. There are other players working with Pyrowave in France, also showing depolymerization of it works. Similar initiatives in US. So no reason to ban it in the end. It's easily sortable, and it's easy recyclables, and the infrastructure is coming on. Construction of an Ersan demonstration plant, we really think it's an asset to also show on pilot scale with tangible input, so not only mass balance, with tangible input on the styrene, a pilot which we can later on and also use for sustainable acrylonitrile and sustainable butadiene in the end. Yeah. Of course, part of the project is also to use that styrene to recycle polystyrene, which we know it works, but it gives additional volumes to our projects. Yeah, it can be used for yogurt pots, but also for other applications. A very big part is the whole sustainability assessment, because the whole acceptance of advanced recycling is really relying on environmental footprints. NGOs blaming industry that it's only using more energy, and in the end it's not recycling, it's energy recovery, it is used as a fuel, it gives other hazards. And it's just by really showing some very thorough and comprehensive sustainability assessments that you can show the opposite. Yeah, so we had already done third-party validated product carbon footprints, where we really can show what are the reductions in CO2. But currently we kicked off now a bigger environmental footprint. Will we work together with recognized players in the fields of plastics to see what is the environmental impact of polystyrene, of ABS, what is the environmental impact of our reductions, and how does that really show that not only on CO2, but also on water, on waste, on emissions, that the whole effort is good. Again, we're already talking here then about a comparison in between fossil production and fossil production with recycled feedstock. What is currently often forgotten and maybe not yet accepted by Europe and by NGOs and stakeholders is the end-of-life savings. Because if you don't incinerate it anymore, incineration gives a lot of CO2. Yeah, you have some energy recovery in some cases, but you get a lot of CO2, and all that you save by recycling it. Yeah, so here a plea to anyone, any stakeholder: please assess the savings over the value chain. Yeah, because that only gives the true added value of circular approaches. For us, very important is communication. So thanks again to the organizers that we can share it. But we make a lot of press releases, articles on really the evidence of polystyrene waste recycling, about the potential of ABS, sustainable ABS. We use it with customers. We talk with the pacts. We talk with foundations, with authorities on that, and the fact that European Union really supports heavily that whole project is, we think, really encouraging. So our aim is here to show ABS as a drop-in solution with advanced recycling for our focus markets. Yeah? So we talk about toys, but we also talk about electronics. We also talk about households, construction, packaging, and automotive. Yeah. So that's where we are now. Yeah. So I think Indaver is really moving up fast with their plant. Yeah. The polystyrene waste is there. The collection is there in Belgium. The sorting equipment is there. More to come from other countries. They are really doing the efforts to start the construction of the plants. Also have already an upscaling plant available. We have shown it already works at lab scale and preparing then for the offtake and pilot scale. And in meantimes, making our low carbon and LCAs over there. Yeah. So we are actually only in the first year, I think first year and a half. So we still have 2 years ahead of us, but I think we are quite good on track and already showing some very promising results. And with this, we hope not only to contribute to the perception of ABS as sustainable material, but also to really help the industry in promoting our advanced recycling solutions. So that was my quick summary of our LIFE Absolutely Circular project. Happy to answer any questions which might come from the audience.
Thank you very much for this good presentation. I don't see any questions for now, but I have one question. You mentioned that already there's a collection strategy. This is part of in the business industrial plan. And you also mentioned the higher efficiency, or actually the higher quality of product that can be achieved with chemical recycling as opposed to mechanical recycling. Do you see mechanical recycling and mechanical recycler as an important step in contributing to the collection scheme? And if so, what is the strategy in terms of volumes and what you expect?
I really like your question. Yeah, I think mechanical recycling and chemical recycling go hand in hand, and they are really complementary. They are not cannibalizing one or another, because in the first step, we always need to look what can we do with mechanical recycling, because that will always be the cheapest, and will always be the lowest carbon footprints, and will always be the fastest. So in the first place, we really support mechanical recycling. However, today and also tomorrow, also mechanical recycling has some limitations.
Correct.
It can go to food grades. It can go to kind of colorings, or to types of solutions where we are not there yet and maybe never get there with mechanical recycling. And on the other hand, we have waste which is simply not good enough for mechanical recycling and which gets incinerated anyhow. And then we need to step in as chemical recycling. We need to take that lower quality of waste, or maybe scrap which is outsorted during mechanical recycling because they are not good enough, and we need to take care, yeah, and go for chemical recycling. It's a bit of a bigger investment than mechanical recycling, be sure, but what is the price if you really can take the lower qualities of waste and bring them to the upper qualities of products? That is really helping us to address the real issue of plastic waste. Yeah, the emissions you have, the landfill you have, with all of that, which is not mechanical recycled. I'm not afraid of waste which is mechanical recycled. It's nice collected, it's nice sorted, it's running well, but all the rest, there chemical recycling can take care of and bring it to the very, very high specifications so that all applications can have a 30% recycled content and all applications can take up their responsibility in the circularity. So I really see it working hand in hand, and we need to boost mechanical recycling further and do everything we can to move that. But we should not be afraid of chemical recycling because it's helping us to address the real problems and also go the extra mile. Yeah.
No, actually, I totally agree with you when you realize the full chemical suite of various elements and compounds that are in plastics by going down and you know, to the almost elemental level, this is pretty much the only way you can get rid of everything. But as a geologist, I was just trying, and you're confirming what I'm hearing, to see if we could do kind of a parallel as, you know, when you have a mining operation, you're doing a concentrate, and this concentrate is not a final product. It goes to the smelter, who goes that last mile to produce that pure metal. But they both work hand in hand. One needs the other, and one makes the other better. So this was really the sense of my question. But I think we fully agree on this one.
And I really like the question, and the reason is why, because advanced recycling is not well enough understood. And it's a bit penalized by NGOs who really think we are just spoiling more energy. It's an excuse of the chemical industry not to do mechanical recycling. It's causing hazardous products. But I think we need to tackle that one by one. We embrace mechanical recycling, but it will not be enough because the targets are really very, very challenging. And we really need to, of course, show what our CO2 and our environmental footprint reductions are, and we only need to become better in them. But we need to give it a chance, because we are at the pilot level. We are preparing upscaled plans. Rome is not built in one day, and the processes need to improve time over time. So it means that the carbon footprint, while scaling up, will improve, while we are reducing our scope 1 and scope 2 emissions, will improve.
Correct.
And that, as a chemical industry, we have a track record on that over the last 30 years to develop processes. But we cannot develop a process in 1 or 2 years. We need to have a bit of time, and really convince and talk, also come out of our tower and talk with all the stakeholders. Like you said, it's really working hand in hand.
Yeah, so it's a good translation. I see that there's a question from the audience from Mr. Kevin Pollemans. Is that correct? If you hear me, please go ahead with your question.
Yes, good afternoon. Thank you very much for this very nice presentation. The only concern that I was I totally agree with all in the way of thinking and the process. The only thing that I was thinking about was that in the end, you see that in packaging, nowadays there's already a big trend away from polystyrene. There's a trend towards much less sustainable packaging away from polystyrene. Do you think your development will come in time to still address this kind of waste as well, to get circular material out of this waste stream?
I think yes, and I tell you why. One, because we can both rely on polystyrene waste. We can go for mechanical recycling and depolymerization. Yet we can also rely on the big volumes of waste, of polyolefin waste, big quantities of waste. And if you paralyze them, our polystyrene can be in the inlet of the pyrolysis units. Up to 20% is feasible if you ask Plastics Energy. And then you go at steam cracker level, you have ethylene and benzene, and we make styrene. So we prefer to make our recycled styrene and recycled polystyrene from polystyrene, because it has excellent environmental footprints. However, we can also rely on the big trends and the mega industry investments. And I think Plastic Europe published it. It's really a huge number of investments that is coming on into chemical recycling. We can also use that to have recycled polystyrene. And that's really an asset, if you can have it from the polystyrene waste and for the polyolefin waste. And then it's a bit the chicken and the egg. The early movers, or the early ones moving away, they will not have it. But the ones staying with us and having confidence in our technology, they will be the first ones to benefit from the benefits from depolymerized styrene. So, and we also think it's a bit chicken and egg, because currently some nations think, oh, we're not going to sort out polystyrene. It's just more expensive. Let's start with the big volumes, the polyolefins first, and then they go for 3 types of PET and 10 types of polyolefins, and then 1 polystyrene is not necessary because it's too expensive. But the opposite is true, because polystyrene is very easy to be sortable, and we have it from our partners, not only in the lab, but really in reality, it's easy sortable. It's certainly not more expensive than another type of PET. and it has an excellent offtake. If you understand, it has a 50% lower carbon footprint than the fossil one. It has not only advantages for the circular economy, but also for the low carbon economy. And we hit 2 flies in one. Yeah, so it's a challenge. It's a challenge against the time. I do agree with that, but I think the technology and the overall approach is at our hands. Yeah, because we can rely on many technologies and many sorting. Yeah.
Great, thank you.
Maybe I have one question for you. What is the quality of the input material in your reactor for depolymerization of the polystyrene? Do you accept some contamination with other polymers?
Of course, yeah, of course. But actually, to be very honest to you, that's actually the whole setup of a demo plant. Yeah. So we have done tests in the lab for years. We had a mini plant for years, so we have tested all qualities of waste already. However, the real setup of a demo plant is to see, okay, what are the benefits of maybe lower quality waste? Yeah, get it done, or maybe to do an additional sorting before, and having the higher yields out. Yeah, it might be good to do additional pre-sorting step before that you have the higher inputs and you need to distill or purify less. We need to define that optimum, to be honest. But of course, we can allow impurities in it. This is of course tested. Your approach need to be robust enough. Yeah, like PET, for instance, is it's not the one we like most in as a contaminant in it. Polyolefins we can easily digest. But we are creating that optimum. Yeah, and an additional pre-sorting step is not difficult, and is also quite cheap actually. So yeah, of course we are looking at bales which have a bit lower quality, but we think it's again the chicken and the egg. If the recyclers and the sorters see that they get more money for the more pure polystyrene, they know how to do it. Yeah, they know how to.
That's the key, because if you ask a very, very high purity, the streams will go directly to the mechanical recycling. But maybe it's also interesting to know what is the value that you can, for example, in the LIFE PlasPLUS, we produce PS. Could it be interesting to go in your process, or is it completely a bad idea, or we have to go to mechanical recycling?
As long as there are no flame retardants in it, we accept. I don't say we cannot get out of flame retardants, but then we come into a total different legal topic, which we don't want to address the first time, because we really would like to have it food grade. I don't say technically it's not possible, that I don't say, but I say for just to get started, we start with really non-flame retardant types of material, and then we are very flexible, flexible.
So your target is the packaging, so to do yogurt to yogurt pots.
No, we're starting from post-consumer waste, yeah, which we can use as well for post-consumer waste, but also some electronics waste that we also use. Yeah. And we just need to be sure there's no flame retardants in it. That's the only criterion.
When you say no flame retardant, it means that it respects the ROHS directive, because no, it's complicated.
Yeah. But then we enter a new field. If we say, okay, we really start working here for the consumer food packaging industry, we'd like to have no. Simply no. Yeah. You can also say, okay, we do another batch maybe later on with ELV waste or other waste which has no flame retardants in it, but there might be some very, 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 very limited volumes in which we clean out, and we use it then back for in a closed loop for the automotive or whatever. That's of course an option, yeah. But today we started with the consumer, with the packaging market or the food market, and there we don't have any discussion on it so far. The technology is as suitable for it.
Okay.
If you count mechanical recycling in the first place, to be honest, yeah. So
understood. Okay.
So it's maybe a question of ensuring that the production line remains clean and verifiably clean
Yes.
for your
Yes.
end product, right?
We are, if we really are going for that high-end markets, and regulation still developing, we really play the safe sides. But technically, that is possible. Technically, it's possible. Yeah.
Okay. And your ABS is not going back to mainly PS is for packaging, not ABS. So maybe because we spoke about also ABS or LIFE PlasPLUS, in this case, ABS doesn't go back to packaging.
No, it's actually open loop recycling. Yeah, it's open loop recycling here. Yeah, not only open loop, because we have it from packaging and we also have it from electronics. Yeah, so we don't take it yet from automotive in it. Yeah.
Okay, perfect. Thank you.
If you can, okay.
Well, thank you very much. I don't see any more questions for now. I guess maybe some will emerge and we'll have a chance to discuss this during the panel. Thank you very much, Petra. So we will now move to the next presentation, which is going to be the third and last presentation of the second session, Plastic Ecosystem Stakeholders. And this is going to be from Mr. Simon van Heijden. Excuse me if the pronunciation is not correct. From Heathland, will be presenting on the MMAtwo project. Simon, if you're there, be my guest.
Thank you, Philippe. So I hope you can hear me.
Yes, we can hear you perfectly.
Okay, very good. So I will just share my screen one moment. So I hope you can share my screen, see my screen.
Yes, we can see your screen perfectly.
Yeah, okay, very good. Yeah, let me introduce myself first. I'm Simon van der Heijden from the company Heathland, recycling company focused on the collection of mainly acrylates and polycarbonates. Recently, we became part of the Trinseo group, which is a producer of virgin PMMA and PC, amongst other materials. And I'm presenting you now the MMAtwo project, because we as Heathland are coordinator and initiator of this project. So yeah, this project is about PMMA. I'm not sure this audience how many companies are working with PMMA, or let's say have dealings with PMMA. But surely, yeah, there are some. And if your company doesn't have dealings with PMMA, what I'm going to present is also applicable for certain other polymers, like polystyrene. There's also it has a similar process possibilities, so it could be interesting as well. So PMMA, it is used in different forms, usually higher end products. So not products and not for packaging or something like that, but usually products with a longer lifespan, 5 years, 10 years, 15 years. Examples are the rear lights of vehicles. Every flat screen has a light guide panel inside of PMMA. Construction, think about construction domes. Sanitary, think about bathtubs. All kinds of displays, shopping displays, signage outside of buildings. So this is a material that most of you will be familiar with, and also known under the trade name plexiglass or perspex. And of course, it became extra famous in the Corona crisis when in a lot of shops there were protective screens made from this material. But from the production of PMMA waste and from PMMA products, there's also a lot of waste, production waste coming just right from the production or from the chain after production. as you can see here on the left, the offcuts of a PMMA sheet, but also at the end of the life cycle, the old car lights, old greenhouse scrap, different kinds of PMMA waste. And at MMAtwo, we try to target both. So first from the production, the production chain to get PMMA waste there as soon as possible. Of course, the majority of the waste can be collected at the end of its lifespan. And that's specifically what MMAtwo is targeting. So that's where we want to get PMMA and avoid it to be disposed or landfilled. Now, PMMA can be recycled. It's not that we have invented PMMA recycling. It's already happening. It can be recycled in two ways. One is mechanically and one is chemically. So mechanically is advantageous because it takes a lot less energy than the chemical recycling. So why not recycle everything mechanically? Well, yeah, you cannot basically. One reason is just because of the colors. When you start recycling mechanically, you're gonna produce a lot of black colored material in the end. And question is if there's so much market for black colored PMMA. But more importantly, there's PMMA in different grades. There's extrusion grade, injection grade, casting grade. When you have material contaminated with casting grade PMMA, it's already not possible to recycle that mechanically. Then you need to depolymerize that because of the molecular weight of the cast PMMA. You need to depolymerize it. And that means you will be adding 2 times energy, 1 time to depolymerize it, 1 time to polymerize it again. But the advantage is you can take out all the additives inside the material, and you can create a very nice closed loop. And PMMA is very suitable for chemical recycling because it unzips very nicely in this process. But if you look at the total amount of PMMA waste, probably 80% of all the PMMA waste has to be recycled chemically. There's no way to recycle that mechanically. Now, the chemical recycling of PMMA, that's also what MMAtwo is focusing on. And that's also what I will be speaking about in the remainder of this presentation. It's also not that we invented that. That's happening a lot, mainly outside of Europe. There's a small amount of chemical recycling of PMMA happening inside of Europe. These are companies using a molten metal technology. So they use a lead bath to recycle that. Most companies are doing that outside of Europe, mainly China, India, Brazil. But that means you need to export your material, and with all the changed regulation that we have seen in Europe, there's focus to recycle waste locally, not to export it all over the world. Many countries also close their border. So the 2 main countries for depolymerization, China and India, close their border for scrap. So this material can no longer go there. So we have a big issue, let's say, in Europe, because we lack the capacity to recycle PMMA here. And that's why this initiative came into life. So we started that from 2018. It's a 4 years project. So now we still have a little bit less than 1 year to go. 8.9 million euros budget, of which 6.6 million granted. And it's a collaboration of 16 partners from 7 different countries. You can see the partners here. So these are big companies, small companies, consultancy firms, academics. UGent is a part of this. Comet is also a partner from us in this consortium. And the objective is to work on one side to work on a new technology, which is, let's say, better than the current technology. So it must be a continuous technology. It must be a lead-free technology. It must be an accessible technology. But to do this, not only with, let's say, a technology provider, but to do that with the whole value chain, so that companies that have scrap can participate, and companies that want to use regenerated MMA can also participate, because since the capacity in Europe is so small, estimated around 8,000 tons per year for waste that we estimate at around 300,000 tons per year. So we only have 8,000 tons capacity to process this 300,000 tons. It's very small. So we don't have the capacity, but we also don't have the outlets. So companies who are working with MMA, they're not used to using recycled MMA. They're used to using virgin MMA. So you need to also take them into the project to make them enthusiastic for this product, and to make sure that you have an outlet for material that you recycle. So here you see the setup of the project. It starts with PMMA collecting of the waste, pre-treatment to make the material suitable for subsequent depolymerization. Then there is a step of purification of the material, and then there are the end users who can use the purified MMA in their products. And as you can see, often the end users are also the companies who have the PMMA waste. And now we're trying to make that into a closed loop. And as an example, we are using old caravan windows that we collect, so the scrap of caravan windows, to depolymerize them and to use that regenerated MMA 100% into a new caravan window, and that's showing the circularity of this material. Yeah, so now I will go through these different steps that you see here: collection, pre-treatment, depolymerization, purification, and end use. Just to give you some idea of progress that we made in this project. So as I said, if you look at PMMA waste, the end-of-life waste should be a lot more than the production waste. But the production waste is much easier to target because you know where this PMMA is produced. So you can just go to those factories and target those PMMA streams. But end-of-life PMMA is much more scattered. 300,000 tons per year. It's a big number, but of course it's a very small number compared to many other polymers. That means that many companies, they don't know about PMMA, or they don't focus on PMMA separation. And that means that a lot of PMMA will in the end be landfilled or incinerated. It will not be separated. So one focus from us was to try and really obtain streams of end-of-life PMMA. There's a couple of examples here, like these PMMA from restaurants or PMMA from highway barriers. But to do that, we cannot do that alone. So we are looking for strategic partnerships, for example, with construction companies. When they deconstruct a building, try and target the PMMA waste there, or with some of the big brands. So big brands, they are very, very conscious of their material and their footprint. So they are also willing to collaborate and see, for example, with Chanel, if there is a new campaign for Chanel products, that we can target the right shops and collect PMMA waste from there. So a big part of this is to try and find out where is this waste, end-of-life waste, and to obtain that through partnerships. Okay, so as you can see here, this is some material that we identified. Our original target was to identify 27,000 tons annually of PMMA waste. At the moment, we identified more. We identified more than 30,000 tons annually. So this is really, let's say, material that we know that is there. It's not theoretical streams. It's something that we know is there. But as you can see, only a small amount of that is end of life, only around 20%, where actually the end of life stream should be much, much bigger. So that's also a focus point within the project. And if you look at that waste, what kind of contaminants it has, now, a lot of contamination comes from PE film. because of protection film on PMMA sheets. We see a lot of PVC, paint, glass fiber, other materials. And of course, there's a contamination inside the material. So colorants, heavy metals that have been used as colorant, additives, let's say impact modifiers. So those are also contaminants, which normally for mechanical recycling wouldn't be maybe can be a problem, but especially for chemical recycling, you know that you are depolymerizing, you will get out all the stuff that was put in originally, and then it's very important to know what kind of possibly harmful substances can be inside that material. So after the collection, we do a pre-treatment, and well, I'm not going to go over all the pre-treatment, but this is just an example. One stream of PMMA that we see a lot is PMMA with PVC. That's because in the casting process of PMMA cast sheets, PVC is used to seal the sheet. When casting the sheet, it's to seal the mold, and that means you have from every factory a lot of PMMA PVC waste. Now, in the past, this material was all exported to China or to India, and there people would manually try to separate this PVC, but that goes with, let's say, a rotating saw. The material gets hot, and fumes can come off it. So it's not a very good way to do it. So we found an alternative to do this automatically within the MMAtwo project. So that's one of the innovations we try to bring about, besides the main innovation of depolymerization. And then you can see in the bottom right what kind of material then we are making. And for example, the fraction D that you can see there, that's a material that we would typically use to depolymerize. So here you can see in collaboration with Comet, we checked how much PVC is left from this automatic separation that we used. And here you can see that the separation was very good, 99.5% approximately of pure PMMA. And actually, we want to go even better than that, because PVC is very harmful to your reactor. When you start depolymerizing and there's PVC inside, you can get hydrochloric acid in your reactor, which is very corrosive to your equipment. So we want to take it out as much as possible. So after we have pre-treated this material, we are going to put it in the reactor, and we're just going to add heat. So it's just a process of adding heat. There's no other substance or booster or something like that we need to add. We just take away the oxygen and we add heat to around 350 or 400 degrees, and then the PMMA polymer starts falling apart into MMA vapor that we then collect and that we then condense, and then you have at room temperature MMA liquid. And the reactor that we are using for that is a twin screw reactor. So you can see it here in the middle. That's the reactor we are using. So it's actually a twin screw that could also be used for mechanical recycling, but this one has been modified to use very high operating temperature and to work, of course, in an oxygen-free environment. And the material is fed in this reactor and then subsequently condensed to get the liquid MMA. Yeah, we found that works very well. It's a continuous system. There's a low amount of material in the reactor at each time, making it very safe. So it's a nice process. Here you see also other types of reactors that are being used around the world. So you see the dry distillation reactor, the lead bath, molten bath reactor. There are reactors with pedals inside or with a rotating screw inside. So these are different types of technologies that can be used, but most of them require a high amount of material to be put inside of the reactor. Many of them require a long residence time, which can cause, let's say, reactions that you want to avoid. So we see many benefits of the twin screw reactor that we are using. And from June 2020, we've been doing several depolymerization trials. You can see by the smiling faces that this trial went very well. Wasn't surprising because the material that we put in was also the best grade of PMMA waste, much better than you would normally get in real life. But okay, this was to try and test how this equipment worked, and we saw that it worked very well. So it was a good base to build on. And then we did more tests, and we ran into a lot more troubles that we then had to fix again. But it's just we did it with different types of materials. Here you can see in the top left the difference between the crude that was coming out from this and virgin MMA. Now here you see this yellow material, that's the crude. It still needs to be distilled to make it of a better quality. But you can see here that the crude was also of very high quality. But that of course has to do with a lot with the input material. We also got crudes that have a much darker color or much more impurities inside. And on the bottom you already see some example of these darker crudes that were made with composite material and also with material from WEEE waste, so light guide panels that are in the televisions and flat screens that we then put into the depolymerization reactor, and that gave this kind of crude material. And here you see another test. So we, after each campaign, we improved the system. We made several adjustments, and this was a test in July last year. It was mainly to have long test runs. So we put in a certain or different types of materials, but the main aim was to check the stability of the system and make sure that it can make runs for a very long time, and that it keeps working very well. So we could do measurements on it and also work towards possible commercial applications, because in the end this is a research project and a European sponsored research project. But one of the aims of this project is to deploy this in a commercial plant in the future, and for that we need to do many tests. And this is then a test we did end of last year in October, and that's when we really put difficult materials, so highly contaminated materials, inside the reactor. Material with glass fiber, material mixed with other materials, polystyrene, other plastics. All kinds of different materials. End-of-life car lights, that's the material that Comet prepared from their vehicle recycling. But inside there can also be polyamide, there can be polycarbonate, there can be some ABS. So let's say highly contaminated streams, and we really were pushing the unit to see what it could still handle and what not. And even PVC, we put in PVC, see how it handled that, and it worked very well, because at the end of the test campaign, the equipment was still working. So we learned a lot. And by the way, here you can see also one of those caravan windows we made. So in the picture on the bottom left, there's one of the caravan windows we made from regenerated MMA. It's an on-spec caravan window made from 100% regenerated MMA. So after this depolymerization step, there's a purification step, and that has to be done by distillation. We are doing that with our partner Spijchem, and Spijchem received different samples from different types of crude MMA, but actually was able to turn all of these samples into A-grade quality MMA. And A-grade, you can see here the purity. So first you have a crude which has around 90% MMA inside, and below you see that the MMA that was refined from this is around 99.8%, so very close to a virgin quality. That means you can keep doing this process, keep recycling PMMA over and over again. The impurities are very minor, less than 0.1%. You see that the yield is very high. Yield of MMA very 95% of the MMA in the crude is taken is yielded, and 85% from, let's say, the totality of crude. And if you look from waste, if you go from waste to purified MMA, you're looking at a yield of around 80%. So it's a really high yield. Those impurities are very important because of REACH regulation. Of course, recycling and REACH is still a little bit a gray area. There's different regulations, exemptions, etc. But it's something that will be changing probably in the next couple of years, and that's why it's important to keep those impurities at a minimum. So then, after we make the purified MMA, the MMA is used into PMMA products. One of them being this caravan window, and this is let's say a test by Delta Glass, testing how that material performs. If it becomes yellow over time, and here we actually see that yeah, they are able to make on-spec caravan windows, and in their testing after X many hours, the yellowing is very limited, meaning that's a suitable replacement of virgin MMA. Then it's also very important to look at the, let's say, odors that are coming from regenerated MMA and PMMA made from that material. In the past, it is known that from regenerated MMA, those PMMA sheets could sometimes cause a very strong odor. MMA itself has a very potent odor. And the issue is when you have MMA and you will polymerize it, if you have some substances that are not MMA, but are maybe some substance that is very close, has a close boiling point to MMA, but you were not able to take it out, it may not polymerize in your sheet. So that means you are left with a sheet in which a very small percentage has not been fully polymerized. That means that sheet will start smelling, let's say, has a very strong smell of MMA. And that's not possible, because it's not good, because if you have a caravan window and you are sleeping in your caravan and the window starts smelling very bad, is not good. So we are doing this kind of test to see if the amount of odor is acceptable, and then you can see that the PMMA that was made from MMAtwo MMA actually has a very low odor intensity. It's worse than virgin for sure, but it's in many cases undetectable, and it's within, let's say, acceptable parameters. And it really depends also on the feedstock. When you use certain feedstock, you can completely exclude it, and some feedstock maybe it cannot be excluded, but it can be purified to a very good amount, and it's much better than other commercial recycled PMMA which is available on the market today. So besides optical application, which is the caravan window, that's an example of an optical application of regenerated MMA. We're also looking at applications in other fields, coatings, paints, but in particular also solid surface, so non-optical applications. And here you see an example of solid surface where Plato Stelma, which is also a partner in the consortium, has been making kitchen sinks from this regenerated MMA, and those kitchen sinks were on spec, so material is very suitable to make, let's say, kitchen sinks or solid surface material. But at the same time, like I said, an important part of MMAtwo is to, let's say, help with the market. If we have a good technology, if we source the waste, but we don't have a market for that regenerated MMA, yeah, then it doesn't work. So it's really finding a market on the local market, European market, and for that we have produced different grades of regenerated MMA that are, and it's possible for interested parties to test with them. Also in this audience, if there are interested parties who work with MMA and want to use regenerated MMA in their products and want to do tests with them, then we welcome that very much to let us know and to make tests with your product. So the impact is very important to see what is the impact of this regenerated MMA first compared to virgin MMA, but also compared to other recycled MMA that's on the market. So compared to virgin, we check the different routes to make a virgin monomer, and we saw that there's a significant impact, so up to 75% reduction. This is then the CO2 emission, but we're also checking water consumption and energy consumption compared to the other recycling techniques, maybe between 20 and 40% improvement. And that, of course, has all got to do with the continuous process and the fact that we don't need to add any other material like lead or any other additive to transfer the heat to the material. So it's a very efficient way of recycling PMMA waste, and it has big advantages compared to virgin MMA and other regenerated MMA. Yeah, so we have online let's say environmental benefits calculator where we check not only CO2 emission but also the water consumption and the energy consumption. This one is not yet finished. Who is interested, I can already provide a web address, but actually it's officially not yet online, but it will be online very soon. And you can see that also on the MMAtwo project website, where we will make a link for that. But at least here you can put in certain parameters that you want, for example, what kind of purity that you want, and you want to compare it to, for example, a recycled process or a virgin process, and what kind of feedstock that you want to use. And then this calculator can provide information about what is the impact. So how much CO2 did you save by using that, and how much water did you save, and how much energy did you save. So that is how we can show to the public that this is really a saving of resources. Now, as this is a European project, we also do a lot of dissemination activities. We publish things on the website, on LinkedIn. We were a finalist last year for Renewable Material of the Year 2021. Unfortunately, didn't win that contest, but at least the fact that we were finalist was already very nice for the visibility of our project. And aside from that, we have several, let's say, scientific papers that have been published by UGent, but also by Arkema in collaboration with the partners. And let's see, yeah. So if you have more information about this, if you have more questions about this project, please contact me as coordinator, or contact Jean-Luc or Maud, or visit our website MMAtwo.eu. And you can also write your company there as an interested party. We can send you the newsletter for this. And that's it. Thank you very much for your attention.
Thank you, Simon. I don't know if you can hear me.
Yes.
Okay, yeah. Okay, our technical team is right on top of things. Thank you very much. That was a great presentation, and it's true that it's very much actual and current theme. As we've all seen these PMMA COVID screens. They've been everywhere. And I think they've made a great publicity for the product. It's nice that you brought that up. I had a question for you, and it's the following. You mentioned that companies which are end users are not used to working with PMMA, and that might be a hindrance for material acceptance. And I wanted to ask you if they could reconsider their position in the light of what Stellantis, our partner, said this morning, that in fact, as a car manufacturer, they've acknowledged the importance of recycled products by creating product specifications applicable to recycled materials. So I'm just wondering if you sense that some of the potential end users might also be working in that direction.
Yeah, so they basically there is a lot of interest in this regenerated MMA, and for example, yeah, automotive producers, they want to become more circular. They want to yeah, use circular raw materials in their products. Yeah, the thing is, yeah, they still of course the quality demands are very high. They want to make sure first that the product is very good. And yeah, even a very small, let's say, substance that you don't want to have in there can already have implications in your for example, what I mentioned with this odor problem. If you have a very small contaminant in there and it doesn't polymerize completely, you may get an odor from that. But I think generally companies are quite open to do that, but it requires testing. They will definitely not switch from virgin monomer to regenerated monomer very quickly. That's a process probably of years to switch. But at the same time, it's also the question of, yeah, in order to make this successful, you need demand. But in order to get demand, you also need the supply, because they once they start building, maybe they need to tweak their production process a little bit to be able to use this regenerated MMA. But if the MMA is not coming, if it's not coming through, then yeah, they think, okay, yeah, they need to be able to rely on both the quality and the quantity, and the quantity needs to be rather big to make it interesting. Compared to virgin MMA, the quantities that we're talking about here, like 30 kilotons per year or something like that, is like a very minor quantity. And you see that yeah, the reliance to have that quantity and to make sure you can always guarantee that quantity, because waste, we cannot make more waste. There's a certain amount of waste and that's it. We cannot just yeah, generate more of that. Yeah, there's a hesitance, so it goes in very slow steps. One is this quality, but also this quantity. We now want to use 1 kilotons of regenerated MMA in our production. Okay, can we really rely on this 1 kilotons? Can we get it this year? And yeah, that's at the moment you cannot. At the moment you have 8,000 tons capacity in Europe for regenerated MMA. So at the moment you cannot rely on it. And even if we let these companies test this material and they say in the end, yeah, it is very good, then they say, yeah, okay, I need 10 kilotons of this, and then yeah, then you need an investment, you need a big factory. So yeah, it's a process, but it's yeah, basically you have demand, but they also need a kind of a big supply, and yeah,
stability in
you
time.
need the stability. Yeah.
Okay.
So it's yeah, it's work in progress, but yeah, we're definitely not there yet.
Okay, thank you. I see that Petra Engelbrecht had a question. Petra, I don't know if you want to ask your question directly to Simon, or
yes, happy to do. First of all,
go ahead.
Yeah, first of all, thanks for the presentation. I think it's a great presentation, and to see similar depolymerization projects popping up, it's really a pleasure. 2 questions. One, I saw also impressive numbers on product carbon footprint reductions, up to 75%. Is that cradle to gate, or is it also including the end of life savings, like not having incineration as a first question. And the second question, I saw also a very interesting comparisons in between technologies. How did the fluidized bed technology compare to the twin screw and to the stirred reactor in terms of operability, yields, and scaling?
Yeah.
Thank you.
Yeah, so for the first question, so the LCA doesn't include, let's say, savings to avoid incineration. So this is excluding this. There could be, if you would include that, then maybe the impact would be bigger. But we didn't include that in this LCA yet.
And on the reactor technologies?
Yeah, and the reactor technologies. Indeed, fluid bed. That's also what we let's say investigated, and also stirred reactor. So fluid bed is actually also a very good technology to depolymerize PMMA. But okay, fluid bed means you have alumina particles or sand particles in there, and they can contaminate. So you need to. The main issue with fluid bed is that the bed can become unstable quite quickly. So if we put in PMMA and it doesn't very quickly, let's say, depolymerize and leave the bed, or if there is more waste, maybe remainders of PE film or other waste, then it can contaminate the bed very quickly. And if the bed gets contaminated, it will collapse. So there were several tests done with PMMA in fluid bed, different designs of fluid bed, also with an inverted cone structure, which should perform a little bit better. But actually, with all of these beds, we had similar problems. And in the end, what we found is that the only way to keep the bed stable is to put in a very small amount of PMMA waste. And then the whole installation becomes very inefficient, because you can only run a very small amount of PMMA waste through your the installation. Then your energy consumption is suddenly very high compared to the amount of PMMA you have been processing. So generally, we found that that's not so suitable. We know that Mitsubishi in Japan they have published that they had at a certain time they had a pilot reactor also based on a fluid bed technology for 1 kiloton per year. And as we understand from the documentation, that plant ran for approximately 30 minutes without problems, and after that was problems all over. So, and they stopped that project in the end. So I don't know exactly the details. They would have to comment on that, but generally we see difficulty with this. Then the stirred reactor. So stirred reactor. So that there's different kinds of stirred reactor. I think maybe you mean the one
reactor. Yes. Yeah.
Sorry, which one?
Just simple continuous stirred tank reactor.
Yes. Yeah. So and you mean the one with lead bath, with a lead bath, for example, the combination of stirred reactor and lead bath, or
yes.
Yeah. The lead bath, actually it works very good, and if you have a stirred reactor, make sure that you have better heat transfer. So it's good to avoid certain heat peaks at some parts of the reactor, which will cause contaminants in your MMA. So it's better to do that, but at the same time, the stirred reactor probably will have a longer residence time, much longer than the twin screw. And in the twin screw, you're talking about seconds. In the stirred reactor, maybe is minutes or hours. So it can be longer. For the let's say, and with the lead, so with the lead reactor, though it works very well, because all your waste will float on top of the lead bath. So you can, but you're still then with the waste, you need to scrape off the waste, and it's lead contaminated waste. And it's also it's not a technology that is typically self-cleaning. So with the technology in MMAtwo, during operation, those screws on the top of the barrel, let's say, you get all the fumes that can be taken away, the MMA fumes, and at the bottom in the barrel you have the solid waste, and that will be pushed out continuously by the two screws to a vessel. So it's a self-cleaning mechanism, and yeah, that's probably not the case in the stirred reactor. It depends on the design, but at least in the lead bath reactor, it's not the case. At a certain time, you need to shut it down, and you need to clean it. So it's not that continuous. Now, if your technology is continuous, that means you have a lower energy consumption generally. So that's a good way. Yeah, in terms of quality, you can make a good quality MMA from different reactors. So different reactors have different advantages and disadvantages, and even with let's say also the lead bath reactor, you can make a very nice quality. If you make a very good distillation afterwards, you can make a very nice quality. But yeah, it may be easier. You have less byproducts probably in this MMAtwo technology than in these two other technologies that you mentioned.
Thank you. I think it's a very, very comprehensive explanation. Really appreciate that kind of sharings. Last question still, what are your current timelines to scale up from pilot scale to the more industrial, semi-industrial scale? So the next step of scaling up?
Yeah, we are having another, let's say, bigger test this year which is basically meant to become as close as possible to commercial conditions. They are not commercial conditions, but in let's say the improvements that we are making, they are already looking at the next step, of course. And after that, so this project ends in September of this year, and after that we would like to have something of industrial scale running at around 18 months, so 1.5 years.
Yeah. Okay. Very interesting. Thanks a lot. Good luck with it.
Thank you.
And as well interested in samples.
Okay. Yeah. So if you then it's good to keep in contact over email.
We also use it in combined Styrenix applications, so it might be of your value if your solution can reach a broader portfolio of products with more demands, etc.
Yeah, that would be very good. So we would be very interested to make let's say collaborative tests then in this, so to provide samples to you for testing it.
Thank you very much, Simon and Petra, for these great questions, presentation, and exchanges. Just a little bit of housekeeping here, where we're due for a coffee break, but given that the discussion is ongoing, our technical team has suggested that we move on to the panel right away. I mean, if it's okay with everybody, that would be fairly appreciated. And also another question for project administration purposes, it would be nice if we could get a group picture, and if everybody could turn up their screen, if it's okay with them, obviously, so that we could get a group picture for this event, which is being undertaken in the context of a LIFE project. And this is the first one. This is our first dedicated event, as Hervé mentioned in his presentation. There will be a second one towards the end of this year, which we hope can be held on site. But yeah, so I think we can move with the panel if everybody's okay with it, or if some people intend to leave before, maybe we can do the group picture. Jerome, I'll leave it up to you.
How can I do that?
Yeah, I think we need the help of our technical person who had requested this, if he's hearing me.
Yes.
Maybe. Okay, there we are, Jérôme. There you
It's
are.
done. I think the pictures are done and
okay, good.
in the box.
Okay, good.
Thank you
So
all.
you had everyone. Okay, it's just that on my end.
Okay.
On my end, I could not see everyone.
We'll do it again.
But if you
Thank
did
you.
that,
Okay, it's better like this. Okay, thank you.
Yeah.
Thank you, Philippe.
Okay, no problem. That's really good. I think if we move with a panel now, and then we'll have a wrap up and closing remark, we might as well. That way, we can free everybody a little bit earlier. Huh? So, Jérôme, I don't know if you intend to use a panel setup again this time.
Yes, I do it again.
Yeah, I believe Esther had to go, but I understand Petra is still here and Simon's here as well. And we have Hervé there. We are in panel mode. So just checking my chat to see if there are any specific questions from the audience that might be used as a Kickstarter, let's say. No, I think some people are kind of leaving a little bit. I saw somebody saying bye here, but yeah, I don't see any specific questions. So I might kickstart with one and maybe get your perspective as plastic experts. And this is just to build on what we discussed with you, Petra, the kind of parallel we can do between the metals industry and the plastic industry. And we first touched on how mechanical recycler were used as concentrate producer to produce feed for the next step in the food chain, which is actually going to treat the material to end up with very much a purified end product, metal in the case of mining, and very pure plastic in the case of the chemical plastic industry. Would you envision, and this I guess is to you both, to Petra and Simon, a situation where we could even push the parallel further? This is a hypothetical question, but if you could push that parallel further, knowing that some smelters, which are the end industry in metal refining, do a blend of natural ores and recyclates, so to speak, okay? And they actually combine primary streams and secondary stream to end up with a marketable product, refined metal in this case. Would this be, could this be envisioned in the plastic industry, in your respective projects, knowing that it's obviously more sensitive, and you said that, Petra, to possible toxic substances, especially if you're targeting a specific market, but would this be possible?
Well, I'm not an expert, and I have not a detailed view on the processes of the metal refinery. However, there will always be a kind of residual waste, which is even hard to combat with chemical recycling. And there perhaps valorization of that streams as energy source might be feasible in the metal industry. On the other hand, I suppose the metal industry might also have CO emissions, not CO2, but CO emissions, which could be a valuable source to be reconverted back by fermentation to monomers, which we then can use for making plastics. So if your question is, can we in the future, not only joining forces within the chemical plastics industry, but also set up collaborations amongst industries like metal and plastics, my answer is yes. Yeah, and to be further explored. However, I would need to have more details of the process of a metal refinery, to maybe learn more about recycling processes and share learnings over there. But maybe the other team has also visions and views on that.
Yeah, so just to understand, in your question, I think I also heard something about, let's say, dilution of the materials. Is it correct? So to let's say dilute the waste with virgin material, or the regenerated material with virgin material, or?
Yeah, in the end, that's what you do, because you actually do a blend of primary sources and secondary sources, the primary sources being naturally more clean in the case of plastics, and you do dilute, whatever deleterious substances there would be in the secondary stream, yes. But the object would not necessarily be to dilute, but to, increase the streams of productions. Yeah. Because
let's say for the regenerated MMA, even though it can be used very well, let's say in 100%, like the caravan window that we show, okay, that's fully made from this regenerated MMA. In practice, you will see that is better to have a little bit less good distillation, for example, have a little bit less good end product. Even you can make a better product, but you will make a less good product, and you will dilute it in the end because it's that's probably cheaper. So that's not. We of course we want to make the best possible end product, but in the end for the customer they will look at the price. They think, okay, we can just dilute it with virgin material and do it like that. So that's a big discussion. Also with let's say, are we going to go for, let's say, the mass balance method, or are we going to actually really use this material direct for, like in the case of the caravan window? There's no mass balance. This is just really taking regenerated MMA, making that into PMMA. So I think, that there will be, let's say, interesting discussions in this field as well. That's a very actual discussion, let's say, in the field of polymers. Okay, well, thank you. I see that Hilde Govaerts may be wanting to ask a question. Hilde, I saw you appear on the screen. Oh, there you are. You're in the panel. Great.
Yes, they invited me to the
Welcome.
panel.
Yes, thank you for being here.
But I think it is very important, especially for flame retardant plastics, not to dilute everything. We really see that it is a disadvantage for all the mechanical properties or FR properties to mix up. So it's, I think it's very important to sort the different plastics very well and not to dilute.
Indeed, that's much better. But if I look currently what's happening in the industry, let's say there's a lot of dilution happening. So I don't know, maybe with of course with flame retardants, it's as far as I know, it's very strictly governed. So you cannot just blend this with that. But especially mechanical recycling, then there's a lot of blending happening.
Yeah, I mean the parallel I was trying to draw has got limitations, obviously. So no, I understand your point of view for sure. And that, if you're in the metals industry, you go back to a very elemental form, which kind of purifies everything, in the plastic industry, you're more like a little bit like the industrial mineral industry, where the mechanical and physical properties are also very important for the product. So yeah.
But in that case, that's where the chemical recycling it's like a catch-all. So for the chemical recycling, at least in PMMA, then you really go back to the monomer. Then you take out all these additives or flame retardants that you had inside. But that's also where you get the real mess, because then you get, let's say, waste from 30 years ago, or maybe long time ago, when when maybe some colorants based on heavy metals or something, maybe they it was common to use them, and all that stuff you will get as your, let's say, side product from the depolymerization process. That can be really toxic substances, and that but it does filter out. So at that step, you do filter out then all these byproducts, and you're really left with a really, let's say, as you call it, elemental kind of raw material.
And is there any possibility that when you're referring to these old plastics that contain substances that are no longer introduced in plastics, so they're kind of remnants, could that be again a parallel that it was initially not intended to do anything with those substances, but since you recover them anyways, because you're going back to the elemental form, can they be of any use at all, or are they doomed to enter landfilling, or is there any commercial application for these inherited substances, let's say?
Yeah, you have a byproduct that it has been heated very well for some time. It's a kind of carbon kind of byproduct, and we within the project are definitely looking at outlets where it can be used. So and then for, let's say, better than just mixing it with concrete, but really to use it as something to improve materials. And for example, the steel production could be a potential outlet to use that carbon in modification of steel. That could be a possibility, but it really depends what's in it. So we are looking at this. We are in that view. 4 years is a very short time to investigate all of this. The technology, the let's say the value chain, and also all these byproducts. But it's something that in this last year we are really focusing on what kind of byproducts can we get from this waste. How can we analyze it? Can we see that it's generally the same material, and can we do something with it? Can we valorize it? Yeah.
Okay. Thanks. That's a very comprehensive answer. I'm going to turn to Hervé just to see if you want to add something to this panel, Hervé, or if the perspective of the mechanical recycler can just add to the debate, and specifically what we are doing with the antimony, because in the case of LIFE PlasPLUS, it's dual material type of recovery. On one end, we're trying to upgrade the plastic, and on the other end, we're trying to upgrade the antimony. So this is, there might be an interesting perspective at this stage. What do you think?
I think that LIFE PlasPLUS is demonstrating that both solutions, also the mechanical recycling for ABS, PS, and FPB, we have this mechanical recycling. But to recycle antimony, we have more chemical recycling step, because we need to do the cracking to liberate the antimony from the matrix in plastic. So
yeah, in this case, very specifically, if we want to get the antimony out, we do have to go through sort of a chemical step, if the pyrolysis and the generation of char with further hydrometallurgy can be considered as such. Yeah.
And we have also to think that, because we don't is that about the flame retardant plastics, we have to destroy, to eliminate the high concern substances, and that's one way is pyrolyze this. So we mineralize the bromine, and we concentrate we mineralize the bromine in the brine, in the salt water, and we have the antimony in the char. So we have to do these steps because, of course, there is still accepted and high value brominated molecules that we can use as flame retardant. But the problem for the recyclers is how to identify and separate flame retardants molecules by molecules, because it's in all streams we have a big mixture of all kind of bromine flame retardant plastics. That's why at the moment it's not possible to. The only way is to separate all the flame retardant plastics together. Between the flame retardant plastics, we cannot separate the good brominated flame retardant from the others. We have to take all together to find a solution.
Yeah, thank you for this this comment. I'm going to turn to the audience and our technical expert to see if there are any contribution from the chat at this point, or if anybody else has a subject that they would like to discuss. I don't think there's much response. So maybe we can end this panel if everybody's in agreement. And I would like to thank everybody, especially the speakers from this afternoon session and the 3 projects that were presented. Plas2B-Clean, MMAtwo, and Absolutely Circular. Very, very nice to have these different plastic streams and see how they can be pushed forward, and to have a perspective on the chemical recycling, because this is really the plus that I see from this session, to see the value of what is being done with this different type of recycling, as a matter of fact. So thank you very much also for allowing us to do this group picture for the project. And I'm going to now turn back to Hervé, who is a project manager for LIFE PlasPLUS, who can wrap up the day and provide some closing remarks. Hervé, the floor is yours.
Thank you, Philippe. So to finish this event, I will finish with the closing remarks on this day. So first, of course, I would like to thank you everyone for their participation. We are happy for your participation. I think a way to properly close this constructive LIFE PlasPLUS dedicated event is to summarize some of the highlights of the day. In this morning session, first, provide us a good overview of what is the European plastics ecosystem. We saw that with Plastics Europe provide us the global matrix, and notably highlighting of the 20 million tons of post-consumer plastic waste collected. So we are working on those tonnage. So out of this 29 million tons, Comet and the LIFE PlasPLUS partners are working on this to increase the recycling percentage of amount. We are constantly stand at 34.6%. It means that the effort is to increase the level of recycling from this collected waste. And about plastic recyclers, I think they focused on more details on the technical plastics, and notably the shredder light fraction from WEEE and ELV treatment centers. This specifically concern Comet and LIFE PlasPLUS partner, which target to upcycling the recycled plastics, specifically by reintroducing ABS, PS, and FPP in the circular economy loops through usage of the same new customer products. Stellantis and CRF demonstrate how the aim to improve the uptake of recycled plastics in the manufacturing of new vehicles. as highlighted, this is particularly important in the light of current supply chain breakdown experienced by automotive manufacturers. Particularly is the fact that Stellantis create product specification applicable to recycled material, thereby announcing the importance of the recycled materials. I think this specification gave added value to recycled product. This is a very good point for the future to design with recycled material. After CAMPINE, who is the largest global player in antimony outside of China, plays a key role in the LIFE PlasPLUS project, which is also aiming to produce high purity recycled antimony master batch of compounds. And antimony, which remains high on the European version of the critical raw material list, is finding new application in products such as liquid metals battery for long-term storage. And the role of synergist in flame retardant products remain antimony-based application. So I think antimony has a good future in the, and of course during the panel of Comet and CAMPINE highlighted to maximize the integration of recycled products in the new consumer products. The recycling approach must focus on trying to constantly upgrade the quality of recycled product. I think for recycling, the quality is the key. Beyond strict financial consideration, this is a corporate approach that must permeate at all levels of the companies involved. So I think we need to increase the quality to be sure to have more recycled material integrated in all kind of goods that we produce. And I think it's all fine my closing remark on this. And what I could add is to speak a little bit about the three last presentation of this afternoon. We saw that we have potential synergies with the project of PlasTubiclean because they are working on ABS and HEPS, and of course they are working together with CAMPINE about the antimony. What also is interesting is to work with Ineos because they have added value on the polymer, on the valorization of HEPS, and it will be interesting to see how we can use our ABS to produce, to mix it with their PS coming from a mechanical, from recycling, from chemical recycling, and to see if there is a potential connection between the two technologies. And MMAtwo is always represented the possibility of chemical recycling, and that's a technique that MMAtwo is showing that chemical recycling offer large possibility in recycling. So now I thank you again for everything, for your participation, and I hope that we will see you again at our next dedicated event when we will finish this project. And in the meantime, all the information, please visit our website because all of this will be put online if you want to view again one presentation. Thank you so much for your presentation, and I hope to meet you soon. Thank you very much.
Thank you everyone. Thank you, Hervé. Thank you very much.
Thank you very much.
Great afternoon.
Thank you. Bye. Bye.
You too.
Thank you.
Bye.
Bye. Thank you.
Bye bye.
Thank you. Bye.
Thank
Nice
you.
session. Thank you.
Bye.
Thank you. Bye.
Thank you. Bye.
Thank you.
Thank you. Bye.